Tonight's story is not about terror or revulsion, but about spreadsheets. Somewhere in a facility that looks more like a food processing plant than a laboratory, technicians are recording numbers in a logbook: date, batch number, radiation dose, number of males produced. The product leaving this factory is not poison or traps, but flies, millions of them, that will mate enthusiastically but produce nothing. Each release is logged with the same bureaucratic care as a postal route: flight path, weather conditions, number of insects scattered over the landscape. Our task this evening is to follow this paperwork from the first case reports of a persistent parasite to the final entry where the pest population reaches zero and stays there. The problem begins with wound reports. In veterinary files and livestock inspection records, the same pattern repeats. An animal with a small cut or tick bite that should heal in days instead develops an inflamed, weeping lesion. The wound grows larger, not smaller. When examined closely, it contains larvae, pale, segmented maggots burrowing deeper into living tissue, feeding as they go. These are not the familiar flies that arrive after death to clean up carrion. These are screwworm flies, whose offspring specialize in living flesh. An adult female lands on any break in the skin, a barbed wire scratch, a birthing trauma, a thorn puncture, and deposits a cluster of eggs. Within hours, the eggs hatch. The larvae immediately burrow inward, rasping away tissue with hooked mouthparts, creating expanding cavities that attract more flies and deposit more eggs. Left untreated, a single infestation can kill a cow, a deer, or occasionally a human. The early case files are full of such reports. Ranchers finding animals too weak to stand, veterinarians debriding wounds full of writhing larvae, economic tallies of lost cattle and expensive treatments. This is the problem statement in the operational binder. A parasite that reproduces efficiently, spreads quietly through any warm region with adequate livestock or wildlife, and resists simple solutions. Traditional pest control tools are already in the file, tried and recorded. Insecticides can be applied directly to animals: dips, sprays, topical treatments, and these kill larvae on contact or prevent flies from landing. Broad applications to pastures can reduce adult fly numbers. Traps baited with meat or chemical attractants catch some adults. Quarantine protocols attempt to contain outbreaks by restricting animal movement. The operational logs show these interventions as jagged lines on population graphs. Numbers drop after intensive spraying campaigns, then creep back up when applications stop or when resistant individuals survive and breed. Insecticides affect non-target species, predatory insects, pollinators, soil organisms, and continuous use fosters resistance. Traps require constant maintenance and only capture a fraction of the population. Quarantines slow, spread but don't eliminate established populations. The cumulative picture in these early records is one of persistent effort producing temporary relief. The pest returns season after season because the fundamental reproductive math hasn't changed. Each female still lays hundreds of eggs. Enough survive to adulthood to replace their parents many times over, and the cycle continues. The insight recorded in the research section of the file is not dramatic but structural. Instead of killing adult flies or their larvae, suppose we interrupt the reproductive equation itself. A screwworm population grows because females mate with fertile males and produce viable offspring in large numbers. If a substantial fraction of the males a female encounters are sterile, incapable of fertilizing her eggs, then many of her matings produce nothing. She lays eggs that never hatch, or hatch into larvae that die quickly. If this happens often enough across the population, the average number of surviving offspring per female drops below the replacement threshold. The population begins to decline not because individuals are dying faster, but because fewer viable young are being born. In the operational notes, this is written plainly: reduce effective reproduction rate below replacement level by saturating the environment with competitive but sterile males. It's a shift from poisoning adults to sabotaging their reproductive success, turning the pest's own mating behavior against it. To produce sterile males, the method involves radiation, not in fields or on animals, but in controlled rooms on insect pupae. The process is logged in the production records with the same attention to detail as any manufacturing operation. Flies are reared in bulk, eggs collected from captive colonies, larvae grown in temperature-controlled trays on meat-based or artificial diets, pupae separated and aged until just before adult emergence. Then batches of pupae are placed in shielded chambers and exposed to carefully calibrated doses of ionizing radiation, typically gamma rays from a cobalt-60 source or X-rays from a machine. The radiation dose is high enough to cause significant damage to the DNA in the fly's germ cells, the cells that will produce sperm, but low enough that the flies themselves remain vigorous. They emerge from the pupal case on schedule, fly normally, feed if food is available, and exhibit standard mating behaviours. The critical difference is invisible. When these males mate, the sperm they transfer to females carry enough chromosomal damage that fertilised eggs fail to develop properly. In the quality control section of the log, each batch is tested. Cohort number, radiation dose applied in greys or rads, sample matings conducted with virgin females, egg hatch rates measured. A successful batch shows hatch rates near zero, often less than 1%, with no compromise in male mating competitiveness. These entries are routine, almost boring. Batch 1243, 50,000 male pupae, 90 givae, sterility 99%, flight activity normal, cleared for release. The rearing facilities themselves are industrial in scale and appearance. Imagine a large warehouse divided into climate-controlled rooms. One section holds trays of larvae, each tray a shallow pan filled with a protein-rich medium that looks and smells like ground meat because it often is, rendered animal byproducts, blood meal, carefully formulated to support rapid larval growth. Technicians monitor temperature and humidity on wall-mounted displays, adjust feeding schedules, and record growth rates. Another section is devoted to pupae. Harvested larvae are separated from their feeding medium, cleaned and spread in climate-controlled cabinets where they undergo metamorphosis. Workers sort pupae by size and development stage, sometimes using mechanical sieves or flotation methods to separate viable pupae from dead or deformed ones. A separate room handles adult flies. Newly emerged insects are sorted by sex. Males and females often differ subtly in size, antennae structure, or emergence timing, and females are diverted back to breeding colonies, while males are collected for sterilisation. The radiation chamber is a small, heavily shielded room with thick walls and interlocked doors. Pupae enter in batches, receive their timed dose, and are removed. After irradiation, male pupae are held briefly to ensure emergence, then packaged for transport. Every stage is monitored and logged. Egg collection counts, larval survival percentages, pupal weights, sex ratios, radiation doses, post-treatment mortality rates. The facility produces sterile males the way a factory produces any commodity, with schedules, quality checks, and detailed records. Quality control extends beyond sterility testing to mating performance. It's not enough that irradiated males produce viable eggs, they must also compete successfully with wild males for access to females. Lab trials simulate field conditions. Equal numbers of irradiated males and normal wild-type males are released into cages with virgin females, and mating pairs are observed. If irradiated males secure matings at rates comparable to wild males, the batch passes. If radiation doses are set too high, males may suffer reduced vigour, slower flight, shorter lifespans, less persistent courtship, and will lose mating contests to wild males, rendering the releases ineffective. The dosing protocol is therefore a balance. Enough radiation to ensure sterility, but not so much that it cripples behaviour. These trials appear in the assurance tables as dry statistical comparisons. Mating Competitiveness Index, 0.922, irradiated versus wild, not significantly different, P are 0.005. When the numbers align, high sterility, normal behaviour, the batch is cleared for field deployment. This is the quiet work that determines success, ensuring that millions of factory-made flies will behave like attractive, capable mates that happen to deliver genetic dead ends. Before releasing a single fly, the operations team maps the target area using field surveys and ecological data. Technicians deploy monitoring traps across the region, small containers baited with decaying meat or chemical lures that attract adult flies. Traps are placed in a grid pattern, checked weekly, and the captured flies counted and identified. This data builds a picture of where the parasite population is concentrated, how dense it is, and how it fluctuates with seasons. Livestock inspections contribute additional information. Veterinarians report new infestations, noting location, severity, and animal type. Climate data informs breeding predictions. Screwworm flies thrive in warm, humid conditions, so seasonal temperature and rainfall patterns suggest when and where breeding will peak. All this information is collated into maps and charts in the operational binder. A target polygon is drawn on the map, often colour-coded by infestation density. Red zones for high populations, yellow for moderate, green for sparse. A release calendar is drafted, which areas to saturate first, how many flies per square kilometre per week, and when to intensify releases ahead of expected breeding peaks. The plan looks like a logistics operation for any large-scale delivery service, just with insects instead of packages. Release logistics are recorded in flight logs that resemble aviation maintenance records. Sterile males are packaged in containers, often chilled to reduce activity during transport, and loaded onto small aircraft. Pilots fly predetermined routes over the target area, releasing flies at regular intervals. The flies are dispersed through chutes or simply dropped in biodegradable containers that open after landing. As the flies warm, they become active and disperse naturally into the environment. Flight paths are planned for even coverage, parallel lines spaced to ensure overlapping dispersal zones, with extra passes over known hotspots. Each mission is logged: date, pilot name, departure, and return times, route flown, number of containers released, weather conditions, wind speed and direction, temperature, cloud cover, and any deviations from the planned path. A typical entry reads: Flight 034, 15 March, Route A7, 120,000 males released, winds light southeasterly, visibility good, no issues. Releases are often weekly or bi-weekly, timed to maintain a high ratio of sterile to wild males throughout the breeding season. In some regions, ground releases supplement aerial coverage. Technicians drive to remote or densely vegetated areas and release flies manually. Every release is another line in the log, another dose of sterile competitors added to the environment. Success is measured not by immediate die-offs, but by gradual shifts in population metrics. Monitoring traps continue to operate throughout the release program, and the flies they catch are analysed. In some programs, sterile males are marked before release, dusted with fluorescent powder, fed dyes that colour their bodies, or genetically tagged with markers. Lab workers examine trap catches under ultraviolet light or through genetic tests, identifying which flies came from the factory and which are wild. The ratio of sterile to wild males in the trap serves as a key indicator. If 9 out of 10 captured males are marked as sterile, the program is achieving a high saturation level, and most matings in the field will be fruitless. Case reports provide a parallel data stream. Livestock inspections note the number of new infestations each month, and these tallies should decline if the technique is working. Veterinary records, wound counts, and larval samples are all tracked. Over months and years, graphs in the operations binder show trends. Wild male counts drop as sterile male releases continue. New infestation cases decline. The lines slope downward with seasonal fluctuations, but the overall trajectory is clear. The system works not through dramatic overnight collapses, but through sustained pressure across multiple generations. Each generation of females encounters mostly sterile males, produces mostly inviable eggs, and the next generation is smaller. Repeat this cycle enough times, and the population enters a downward spiral. The mathematics underlying this decline are simple and appear in the operational manual as a boxed note. A pest population persists when each generation replaces itself, when each adult, on average, produces at least one surviving offspring that reaches adulthood and reproduces. This is the replacement threshold, often symbolized as R equals 1. If the effective reproduction rate exceeds 1, the population grows. If it falls below 1, the population shrinks. The Sterile Insect Technique manipulates this rate by reducing the fraction of matings that produce viable offspring. Suppose a typical female mates multiple times during her life, and, under normal conditions, produces 200 eggs that yield 20 surviving adults, giving an R well above 1. But if 3/4 of the males she encounters are sterile, then even with multiple matings, the average number of viable offspring might drop to just 5 adults. If this happens across the whole population, R falls below 1, and each generation is smaller than the last. The tipping point is reached when releases maintain a sterile to wild ratio high enough that R stays suppressed generation after generation. In the manual, this is summarized in a small equation and a guideline. Maintain release rate such that sterile wild ratio exceeds 10:1, harm 1, decline inevitable. It's a quiet rule, grounded in population dynamics, that guides release densities and schedules. Eradication, when it comes, is quiet and appears as zeros in the data tables. Monitoring traps return week after week with no wild flies, only sterile males or nothing at all. Livestock inspections report no new cases. Veterinarians find no fresh infestations. Repeated surveys across the target area confirm that wild populations have fallen below detectable levels. There is no single dramatic moment, no ceremony. Instead, there are cautious notes in the operational log. Wild population, below detection threshold for 12 consecutive weeks. Eradication status, provisionally achieved, continue surveillance. The emphasis is on verification and vigilance. Releases may be scaled back, but often continue at lower levels as a precaution, especially near border areas where reinfestation from adjacent regions remains a risk. The flight logs shift from heavy saturation schedules to maintenance routes, and the graphs plateau at 0. This is success measured in absences. No larvae in wounds, no calls from distressed ranchers, no entries in the case files. The logbook records the transition from active suppression to long-term monitoring, a shift marked by reduced flight hours and stable zero case counts. Many programs don't stop at eradication in one area, but expand their operations progressively, pushing the pest's range back toward geographic barriers that prevent easy reinvasion. The operational maps show this as a moving frontier. A cleared zone expands year by year, with heavy releases along the advancing edge and maintenance releases forming a barrier behind the front. Geographic features help. Deserts, mountain ranges, cold climates where the pest cannot survive, and programs aim to compress the pest's range until it reaches such a barrier. Once confined beyond the barrier, occasional monitoring and small-scale releases maintain a buffer zone that prevents reintroduction. In the log, this appears as evolving release schedules, initial saturation campaigns in new territories, consolidation phases where release rates stabilize, and eventual transition to border maintenance mode. The maps update year by year, showing expanding cleared zones shaded in green and shrinking infestation areas shaded in red. The expansion is methodical, patient, and thoroughly documented. The secondary benefits of these programs accumulate quietly in the margins of annual reports. Livestock health improves. Fewer animals suffer painful infestations, weight loss from parasitic stress decreases, and mortality rates drop. Ranchers spend less on veterinary treatments, and fewer animals are culled due to untreatable wounds. Economic analyses show increased productivity, more calves born healthy, better weight gains, higher meat and hide quality. Export markets become more accessible because regions free of screwworm can certify their livestock as parasite-free, meeting international trade standards. The environmental side effects are minimal compared to broad-spectrum insecticide use. Sterile males are just flies, adding no toxins to soil or water, affecting no non-target species beyond the brief interactions of courtship. The reduction in chemical pesticide applications appears as a line item in the environmental assessment section. Fewer litres sprayed, lower residues detected in tissue samples, fewer complaints about drift or runoff. Animal welfare improves invisibly. Wounds that would have become infested now heal cleanly. Suffering that would have occurred simply doesn't. None of these benefits make headlines. They appear as numbers in tables, small percentage improvements that compound over years and across regions. The word nuclear or radiation in the program's name often raises concerns, and the operational manual addresses this plainly in a safety section. The radiation used to sterilize flies is applied in controlled, shielded facilities to insect pupae, not to fields, animals, or people. The doses are calibrated to damage insect reproductive cells, nothing more. Once sterilized, the flies themselves are not radioactive. They carry no residual radiation and pose no hazard to anything they contact. They are ordinary insects with ordinary lifespans, differing from their wild counterparts only in the viability of their sperm. Radiation safety procedures are standard. Equipment is calibrated regularly, shielding is inspected, worker exposure is monitored with dosimeters, and all protocols follow guidelines established for medical and industrial radiation use. The logs include radiation safety checklists alongside insect rearing checklists, treating the technology as another tool requiring routine precautions. The irony is that a technology associated with reactors, weapons, and cancer treatment also has this mundane, peaceful application. Preventing parasitic flies from reproducing by exposing pupae to controlled doses in a concrete room, then releasing the resulting adults to mate harmlessly in the open air. The same basic template, rearing, sterilizing, releasing, monitoring, has been adapted for other pest species, and the operational archive now includes tabs for multiple programs. Fruit flies that damage citrus and stone fruits have been targeted with similar methods. Mass rearing in facilities that smell of fermenting fruit instead of meat, sterilization protocols adjusted for smaller, faster developing insects, releases timed to orchard bloom cycles. Mosquito programs in pilot stages follow the same structure. Larvae reared in trays of nutrient-rich water, males sterilized or engineered for reproductive incompatibility, releases focused on urban areas with high disease transmission. Tsetse flies, cotton pests, olive flies. Each species requires its own rearing techniques, diet formulations, and release strategies, but the operational logic remains consistent. The logbooks for these programs mirror the screwworm template: production runs, quality assurance tests, flight schedules, population monitoring, and trend graphs. The technique scales across pest types wherever mass rearing is feasible and where saturating an area with sterile insects is logistically practical. Each new program adds its own data to the archive, expanding the library of quiet successes. The human element of these operations rarely appears in the headlines, but fills the margins of the operational records with small notations. Pilots log thousands of flight hours, becoming intimately familiar with landscapes they survey from the air, learning where cattle congregate, where wild deer populations gather, which valleys hold moisture longer and might harbour persistent breeding sites. They adjust for weather, reroute around storms, compensate for wind drift to ensure even distribution. Their notes occasionally include observations beyond the mission parameters: observed large herd near waypoint 7, possible monitoring site, or heavy vegetation in sector 12 may require ground supplementation. These are professionals who understand that their cargo is not inert but living, that timing matters, that a delay of hours can mean a batch of flies emerges in the wrong conditions and fails to disperse properly. Ground crews who check monitoring traps walk the same routes week after week, learning the rhythms of the land. They note which traps consistently attract more flies, which locations seem to be hotspots for wild activity, where terrain makes access difficult and alternative methods might be needed. Their field notebooks contain observations about local wildlife, vegetation changes, seasonal patterns in livestock movement, details that inform strategic adjustments. When trap counts begin to drop, these workers are often the first to notice the trend, the first to see the practical result of months of sustained releases. They record the numbers dispassionately, but there's a quiet satisfaction in tallying zeros where once there were dozens of wildflies. Laboratory technicians who process trap catches work in small rooms that smell faintly of preservatives and the chemical markers used to tag released insects. Under microscopes and ultraviolet lights, they sort through specimens, distinguishing sterile from wild, recording counts, preparing samples for genetic analysis when programs use molecular markers. The work is repetitive and requires attention to detail. A misidentification could skew the ratio calculations that determine whether release rates need adjustment. Their datasheets feed directly into the population models, and an accurate count this week influences next month's release schedule. They are links in a chain that extends from the rearing facility through the sky to the monitoring grid and back to the planning tables where strategists decide whether to intensify, maintain, or scale back operations. The veterinarians and ranchers who report cases, or increasingly report the absence of cases, provide ground truth that validates the models. A rancher who once found infested animals monthly and now goes seasons without a single case becomes a data point in the success column, but also a human story of relief and recovered productivity. Veterinarians who spent years treating painful infestations, debriding wounds, administering systemic medications, euthanizing animals too far gone to save, these professionals notice when the character of their practice changes. Calls about suspected infestations become rare, then vanish. Young veterinarians in cleared regions may complete their training without ever seeing a live case of the parasite their predecessors dealt with routinely. This generational shift appears in the records as declining case counts, but it represents a fundamental change in the burden of animal care in affected regions. International cooperation adds another layer of complexity to the operational records. Screwworm flies don't respect borders, and a cleared region remains vulnerable if neighbouring areas still harbour wild populations. Coordination meetings produce memoranda of understanding, shared protocols, joint monitoring efforts along border zones. One country's rearing facility might supply sterile males for releases in an adjacent nation's territory under mutual agreements. Flight logs note when aircraft cross international boundaries, when ground crews operate in coordinated buffer zones, when data sharing protocols are activated. The paperwork multiplies: customs documentation for transporting live insects, permits for aerial operations in various jurisdictions, agreements on cost-sharing and technical assistance. Yet the operational logic remains the same: saturate the environment with sterile males, monitor the results, adjust as needed, and gradually expand the cleared zone regardless of political boundaries. Long-term maintenance of eradicated zones requires a different operational mindset than initial suppression campaigns. Once wild populations reach zero, the program shifts from attack to defense. Surveillance becomes the primary activity. Monitoring traps continue to operate, livestock inspections remain routine, and any suspected reintroduction triggers immediate investigation and response. Maintenance releases along border zones continue at lower levels, creating a permanent barrier that prevents recolonization from areas beyond the cleared region. The rearing facilities operate at reduced capacity, maintaining breeding colonies and production capability, but not running at full scale. Workers rotate through refresher training to maintain skills that may not be needed for long periods. The budget shifts from intensive operations to steady-state maintenance, and the operational logs become more sparse, long stretches of routine surveillance punctuated by occasional responses to suspected detections that usually turn out to be false alarms or isolated vagrants that pose no real threat. The financial records associated with these programs tell their own story of cost-benefit calculations. Initial capital investments are substantial: building rearing facilities, acquiring radiation sources, purchasing aircraft, training personnel, establishing monitoring networks. Operational costs run year after year: feed for larvae, electricity for climate control, fuel for flights, salaries for staff, equipment maintenance. Accountants track these expenditures in detailed ledgers. Set against these costs are the economic benefits: reduced livestock mortality, decreased veterinary expenses, increased productivity, expanded market access, reduced spending on chemical insecticides. Economic analyses appear in reports to funding agencies, showing that the investment pays for itself over time through accumulated savings and increased agricultural output. The return on investment is calculated in years rather than months, but the math is compelling. Spending on sterile insect programs is dwarfed by the economic damage prevented. Tables compare scenarios with and without intervention, showing diverging trend lines where maintained programs keep losses near zero, while hypothetical uncontrolled populations cause escalating damage. Training programs for new personnel add standardization across facilities and regions. Manuals detail every procedure from egg collection protocols to flight path planning. New technicians shadow experienced workers, learning to judge pupil quality by appearance, to calibrate radiation equipment, to spot signs of disease or stress in breeding colonies. Pilots receive specialized instruction in low-altitude dispersal techniques, learning to compensate for wind, to recognize landmarks in their assigned territories, to troubleshoot equipment issues mid-flight. Laboratory workers train on identification keys, learning the subtle differences between screwworm species and similar-looking but harmless flies, practicing until they can sort trap catches efficiently without errors. This institutional knowledge, captured in training videos, reference guides, and hands-on mentorship, ensures that programs can continue as staff retire or transfer. The continuity is essential. A program that eliminates a pest over decades cannot afford to lose critical expertise to personnel turnover. Archival records from early pilot projects reveal the learning curve involved in developing effective protocols. Initial attempts used lower radiation doses, producing males that were only partially sterile, and occasionally produced viable offspring, undermining the program's effectiveness. Trial and error determined optimal dose ranges. Early release strategies scattered flies uniformly across landscapes, but data showed that targeted releases in high-density areas produced better results. Monitoring initially relied solely on case reports, but the addition of systematic trapping grids provided earlier warning of population trends. Each lesson learned was documented, analysed, and incorporated into revised protocols. Reading through these early records is like watching a methodology mature. Initial uncertainty, experimental adjustments, gradual refinement, eventual standardization. The modern operational manuals are distillations of decades of accumulated experience, each section representing problems solved, mistakes corrected, efficiencies gained. Public communication about these programs is carefully managed and appears in outreach materials that balance transparency with simplicity. Brochures explain the technique in accessible terms, emphasizing safety and environmental benefits. Ranchers receive updates on program progress, maps showing cleared areas, guidance on reporting suspected cases. Local media outlets occasionally run features during campaign launches, filming rearing facilities and interviewing program managers. The messaging is consistent. This is a proven technology, environmentally sound, economically beneficial, and continuously monitored for effectiveness. Public cooperation is essential. Ranchers must report cases, landowners must allow trap placement, communities must understand why small aircraft are flying regular patterns overhead. The communication logs show presentations to agricultural associations, school visits to rearing facilities, question and answer sessions addressing concerns about radiation or genetically modified insects. The latter, a misconception that must be corrected. Radiation sterilization is not genetic modification. The psychological shift from viewing these programs as experimental interventions to accepting them as routine infrastructure takes time and appears indirectly in the records. Early documents show cautious optimism, contingency plans, frequent reviews of whether to continue. Later records assume continuity, plan for decades ahead, discuss maintenance as a permanent operational requirement. This transition from temporary project to permanent fixture mirrors the way other public health interventions, vaccination programs, water treatment systems, disease surveillance networks, become invisible infrastructure that societies depend on but rarely think about. The flies continue to be released, the traps continue to be checked, the data continues to be recorded, and the zero case counts continue year after year, fading into the background of normal agricultural operations. As the story draws to a close, consider the peculiar heroism at the centre of this operation. The agents of eradication are not scientists or pilots or policymakers, but millions of ordinary flies that are, in a fundamental sense, failures. They emerge from their pupal cases, spread their wings, and fly into the world with all the instincts and behaviours of their wild relatives. They search for mates with the same urgency, court females with the same rituals, and mate with the same apparent success. But their contribution is an absence. Every mating that produces no viable offspring, every female that lays eggs that never hatch, every potential next generation that fails to materialize. These flies have no awareness of their role. They live their brief lives, a few weeks at most, seeking the same evolutionary goals that drive all insects, and they die without knowing that their reproductive emptiness is precisely what makes them valuable. They are foot soldiers in a campaign they cannot comprehend, flying sortie after sortie, generation after generation, until the parasite population they infiltrate collapses under the weight of accumulated sterile matings. In the final pages of the operational log, the graphs flatten. Wild fly counts hover at 0. Livestock infestation reports remain blank month after month. The rearing facility shifts to standby mode, maintaining a small breeding colony in case future outbreaks require renewed releases, but the main production lines go quiet. The flight schedules thin out, reduced to occasional surveillance missions. The maps show large regions shaded green, cleared, monitored, safe. The parasite that once caused immense suffering and economic loss has been paperworked out of existence, one sterile mating at a time, each recorded in a flight log that reads like a delivery manifest. There were no battles, no dramatic confrontations, no explosive interventions, just patient, methodical application of reproductive math, supported by millions of unaware insects doing what insects do, and an operations team logging every release, every trap count, every zero on the graph. The legacy of these programs extends beyond the immediate pest they target. The methodology, mass rearing, targeted sterilization, systematic release, continuous monitoring becomes a template applicable to other species, other regions, other problems. Agricultural researchers study the model for managing crop pests that develop resistance to conventional insecticides. Public health officials examine it for vector control in disease-endemic areas. Conservation biologists even consider variations for managing invasive species that threaten native ecosystems. The operational framework, refined through decades of screwworm control, offers a proven alternative to chemical warfare against pests, using biology against itself, turning reproduction into a weapon by rendering it ineffective. The workers who operate these programs rarely seek recognition, and their names don't appear in the summary reports that circulate among policymakers. Yet their expertise, knowing how to judge when pupae are ready for irradiation, understanding how weather patterns affect dispersal, recognizing subtle signs that a breeding colony is becoming inbred and needs genetic refreshment, represents accumulated knowledge that cannot be easily replaced. Some have spent entire careers in these facilities, watching technologies improve, seeing programs expand from pilot projects to regional campaigns, training successive generations of technicians. Their retirement poses institutional risk. Documentation helps, but some knowledge is embodied in practice judgment that comes only from years of experience. Succession planning appears in administrative records, ensuring that critical skills transfer before key personnel depart. The infrastructure supporting these operations is itself a quiet achievement. Rearing facilities in remote locations require reliable electricity, clean water, climate control systems that can maintain precise conditions year-round, supply chains for specialized feeds and equipment. Building and maintaining this infrastructure in developing regions, where programs are often most needed, requires partnerships between governments, international agencies, and agricultural organizations. Funding flows through complex channels: government appropriations, international development grants, industry contributions from livestock associations that benefit from eradication. The financial architecture supporting these programs is documented in budget reports, grant applications, audit records, paperwork ensuring that operations continue smoothly despite changes in political priorities or economic conditions. Data management has evolved from paper logs to digital databases, though the fundamental information collected remains consistent. Modern systems allow real-time updates from field teams, automatic population modelling based on incoming trap data, predictive analytics that forecast when and where release intensification might be needed. Geographic information systems layer multiple data types onto maps, trap locations and catches, release points and densities, topography and vegetation, livestock distribution, weather patterns. Analysts can query these databases to answer questions that would have required weeks of manual record searching in earlier eras. Which areas showed persistent wildfly activity despite intensive releases? How did case rates correlate with seasonal rainfall variations? What were the optimal release densities for different terrain types? This accumulated data represents not just operational history, but a scientific resource for understanding insect population dynamics, dispersal patterns, and the factors influencing program success. As you settle towards sleep tonight, imagine those stacks of logbooks and the graphs they contain. Picture the quiet rooms where flies are reared under controlled conditions, the shielded chambers where pupae are irradiated, the small planes flying low over pastures, scattering insects that will mate but produce nothing. Think of the ranchers who no longer find wounded cattle infested with larvae, the veterinarians whose case files thin out, the children who grow up never knowing that a flesh-eating parasite once plagued their region. The sterile flies continue to be released in buffer zones, maintaining a barrier against reinfestation, their flight paths logged with the same bureaucratic precision as always. The operational manual sits on a shelf, a thick binder full of protocols, schedules, and data tables, ready to be opened again if needed, but mostly serving as a testament to what can be achieved with patience, careful record-keeping, and an elegant manipulation of reproductive biology. Somewhere, tonight, a technician is filling out a form. Batch number, emergence rate, quality check passed. A pilot is reviewing tomorrow's flight plan, tracing fingers along a map of familiar routes. A laboratory worker is sorting trap catches under a lamp, recording counts that will feed into next week's population model. A rancher is checking livestock in a pasture where decades ago infestations were common, but now a memory is recorded only in archived case files. These activities continue in the background of agricultural life, unglamorous but essential, protecting against a resurgence of a pest that biology and bureaucracy combine to eliminate. The story ends not with a bang, but with a series of zeros, each one a quiet victory, each one another line in a very boring, very effective flight log. Sleep comes easily when imagining such methodical, peaceful victories, problems solved through understanding, patience, and millions of small interventions that accumulate into definitive success. The next story is about to begin. Please relax and enjoy. Opening this file feels like pulling up a maintenance log rather than reading mythology. Black holes are not cosmic monsters. They're entries in the universe's catalogue of extreme objects, end states that appear when certain massive stars exhaust their fuel and collapse past every known support mechanism. This is a life cycle report, a bureaucratic recounting of one black hole's journey from birth in the core of a dying star, through long periods of quiet accretion and occasional mergers, to an evaporation so gradual that the numbers involved lose all human meaning. Each stage follows specific physical rules, equations that astronomers and physicists have tested and refined, and the story is less about drama than about watching those rules play out over timescales that dwarf civilizations. Begin with an ordinary massive star, the kind that lives for only a few million years before its fuel runs out. Picture a self-gravitating ball of hot plasma, hundreds of thousands of kilometers across, with temperatures in the core reaching tens of millions of degrees. Gravity pulls every bit of matter inward, trying to collapse the star into a point, but pressure from nuclear fusion pushes outward, holding the structure up. This balance is called hydrostatic equilibrium, and you can think of it as a competition between two gradients, the inward pull of gravity and the outward push of pressure. Imagine tiny shells of star material at various depths. Each shell feels gravity tugging it toward the center, and pressure from the hotter, denser layers below pushing it up. In equilibrium, those forces match at every radius. As long as fusion in the core releases enough energy to maintain that outward pressure, the star's life cycle file is stamped with the status of stable. The star may spend millions of years in this state, quietly fusing hydrogen into helium, with its internal structure adjusting smoothly as fuel is consumed and new layers begin to burn. Nuclear fusion is the star's core algorithm for converting mass into energy. In the simplest version, protons, hydrogen nuclei, collide and eventually fuse into helium through a series of reactions. The proton-proton chain is one pathway. The CNO cycle, which uses carbon, nitrogen, and oxygen as catalysts, is another that dominates in more massive stars. Each fusion step releases energy according to Einstein's famous relation, where a tiny loss of mass translates into a large amount of energy because the speed of light squared is an enormous conversion factor. For stars more massive than the Sun, higher core temperatures allow additional fusion stages to run. After hydrogen is depleted in the core, the temperature and pressure can rise enough to ignite helium burning, producing carbon and oxygen. Then, if the star is massive enough, carbon can fuse to produce neon, sodium and magnesium. Oxygen fuses to make silicon and sulfur, and so on. In the life cycle report, each fusion stage is logged as a fuel upgrade, with approximate core temperatures and timescales written in the margins. Hydrogen burning might last a few million years for a very massive star, helium burning perhaps 500,000, and each successive stage becomes shorter and hotter, the star racing through its remaining options. Eventually, the star builds an iron core at its center. This is a crucial turning point, and it shows up in the report as a red ink note. Earlier fusion reactions release energy because the resulting nuclei are more tightly bound per nucleon than their reactants. Fusing light elements into heavier ones up to iron increases the binding energy per nucleon, freeing up energy in the process. But iron sits near the peak of the binding energy curve. Fusing iron into heavier elements does not release energy. It would require energy input instead. The core's fusion algorithm has reached a dead end. Iron accumulates, and although the outer layers of the star may still be fusing lighter elements in shells around the core, the iron itself provides no support. The core's pressure budget is quietly running out, and the life cycle file notes that the clock is ticking toward a structural failure. To understand what happens next, consider the idea of degeneracy pressure, a quantum mechanical support system that can hold up certain objects even without fusion. Electrons obey the Pauli exclusion principle, which forbids two electrons from occupying the same quantum state in the same region of space. When matter is compressed to high densities, electrons are forced into higher and higher energy states, and this creates an outward pressure that does not depend on temperature. Electron degeneracy pressure is what supports white dwarfs, the remnants of lower mass stars that never get hot enough to fuse carbon and oxygen. For a while, as the iron core grows, it can be supported by electron degeneracy pressure. But there is a limit. The Chandrasekhar limit, about 1.4 solar masses, is the maximum mass that electron degeneracy can hold up. In the life cycle report, an entry tracks the core mass as it edges closer to this critical line, and once the core exceeds the limit, collapse becomes unavoidable. When the iron core crosses that threshold, the star's operating limits are suddenly violated. Electron degeneracy pressure can no longer resist the inward pull of gravity, and the core collapses. This happens fast, within a fraction of a second, with the inner core contracting at a significant fraction of the speed of light. The density rises so high that protons and electrons are squeezed together, merging into neutrons and releasing a vast flood of neutrinos. The core compresses to nuclear densities, where matter is packed as tightly as in an atomic nucleus, and the composition shifts to neutron-rich material. In the report, this phase is a short, intense entry. Core contraction to nuclear densities, composition transition to neutron matter, enormous neutrino burst logged. The neutrinos carry away most of the energy released by the collapse, streaming out through the star almost unimpeded because they interact so weakly with ordinary matter. At nuclear densities, the collapse is halted, at least momentarily. Neutron degeneracy pressure and the repulsive character of the strong nuclear force at short distances create a stiffening in the equation of state, and the core bounces. This bounce, aided by the pressure of the neutrino field and other complex processes that are still debated, launches a shockwave outward through the overlying layers. If conditions are right, the shockwave gains enough energy from neutrino interactions and other mechanisms to blow off the outer envelope of the star as a core collapse supernova. The explosion is spectacular, briefly outshining an entire galaxy, and the outer layers are expelled at thousands of kilometers per second, enriching the surrounding gas with heavy elements forged in the star's life and in the violence of the explosion itself. But the life cycle report is more concerned with what happens at the center. The remnant left behind depends on the mass of the collapsed core. If the core mass is below another limit, the Tolman-Oppenheimer-Volkoff limit, around 2 to 3 solar masses depending on the equation of state of nuclear matter, then neutron degeneracy pressure and the strong force can support the remnant as a neutron star. If the core mass exceeds even that, neutron degeneracy fails, and there is no known force or pressure that can halt the collapse. The object continues to contract past all known states of matter, and the file is updated. Object status changed to black hole. All supporting pressures exceeded. Collapse past visible surface ongoing. Now the life cycle report must define what a black hole actually is. The key concept is the event horizon, the boundary beyond which not even light can escape. For a non-rotating, uncharged black hole, the simplest case, this boundary lies at the Schwarzschild radius, given by a straightforward formula. The Schwarzschild radius equals 2 times the gravitational constant times the mass, divided by the speed of light squared. Each symbol has a clear meaning. The gravitational constant is a fundamental number that sets the strength of gravity. The mass is the total mass of the black hole, and the speed of light is the ultimate speed limit in the universe. The formula tells you that the more mass you pack into a region, the larger the radius at which the escape velocity reaches the speed of light. For a black hole with the mass of the Sun, the Schwarzschild radius would be about 3 kilometers. For a supermassive black hole with 1 billion solar masses, the radius scales up to billions of kilometers, comparable to the size of our solar system. In the life cycle report, the black hole is logged with its mass and the corresponding event horizon radius. There is no surface in the usual sense, no solid boundary you could touch, just this defining scale that separates the interior from the exterior. What lies inside the event horizon is more mysterious. In classical general relativity, the equations describe the mass as being concentrated into a singularity, a region where density and curvature of space-time become infinite. This is where the mathematics breaks down, like encountering a divide by zero error in a computer program. Physicists suspect that a complete theory of quantum gravity would smooth out the singularity, replacing it with something finite and well-defined, but we do not yet have that theory. String theory, loop, quantum gravity, and other approaches suggest possible resolutions, but none are confirmed or complete. In the life cycle file, the singularity is marked with a note: "Physics incomplete here, pending research." It is a placeholder, an admission that the report cannot be fully detailed at the very center, even though the rest of the system is well documented. One common misconception about black holes is that they exert some special kind of suction, pulling in everything around them like a cosmic vacuum cleaner. The reality is calmer. Far from the event horizon, a black hole's gravitational influence is exactly what you would expect from any object of the same mass. If you replace the Sun with a black hole of equal mass, Earth's orbit would remain essentially unchanged. We would lose sunlight and freeze, but we would not be pulled into the black hole. Gravity follows the same inverse square law, whether the source is a star, a planet, or a black hole. The file includes a clarification. For distances much larger than the Schwarzschild radius, the gravitational field behaves like that of any mass of the same amount. Black holes are extreme only in the sense that they allow you to get much closer to the mass than you could with a normal star. And it is in that close-in region that the effects of strong gravity become dramatic. General relativity also predicts gravitational time dilation, an effect that becomes important near the event horizon. Clocks deeper in a gravitational field run slower relative to clocks far away. Imagine two observers, one hovering just outside the event horizon and one far away in a region of weak gravity. The distant observer would see the hovering observer's clock ticking more and more slowly as the hovering observer approaches the horizon. Signals sent from near the horizon would be redshifted, their frequency stretched to lower values, and the light would appear dimmer. From the hovering observer's point of view, their own clock feels normal. Time passes as usual for them. But looking outward, they would see the distant universe's clocks running faster, events in the outside universe appearing to speed up. Both perspectives are correct within their own reference frames. In the paperwork metaphor, two observers are filling out time logs that disagree about how much time has passed and the equations of general relativity account for this difference precisely. The report notes that this is not an illusion or a trick of perception, it is a real effect of curved space-time. As you approach a small black hole, you would also encounter intense tidal forces. Gravity changes rapidly with distance, and the gravitational pull on your feet, if you're falling feet first, would be noticeably stronger than the pull on your head. This difference in acceleration stretches objects along the radial direction and compresses them in the perpendicular directions. The effect is nicknamed spaghettification, and it is not some mysterious extra force but simply the gradient of the gravitational field. Mathematically, it is the derivative of the acceleration with respect to position, a measure of how quickly gravity changes from one point to another. For a stellar mass black hole with a few times the Sun's mass, these tidal forces become lethal well before you reach the event horizon, tearing apart any object that ventures too close. For a supermassive black hole with millions or billions of solar masses, the Schwarzschild radius is so large that the tidal forces at the horizon can be quite gentle. An astronaut falling into a supermassive black hole might cross the event horizon without immediately noticing destructive effects, experiencing a longer journey inward before the tidal gradients become overwhelming deeper inside. The report logs tidal force estimates for different black hole masses, noting where the gradients exceed structural tolerances for various materials. Black holes can be categorized by mass, and the life cycle file includes a taxonomy. Stellar mass black holes form from individual massive stars and typically have masses ranging from a few to a few tens of times the Sun's mass. These are the black holes produced by core collapse supernovae, the direct descendants of the most massive stars in the galaxy. Intermediate mass black holes, if they exist, would have masses in the hundreds to thousands of solar masses. Evidence for this class is less certain, but they might form in dense star clusters through repeated mergers or through the direct collapse of very massive stars in the early universe. Supermassive black holes, with masses of millions to billions of solar masses, are found at the centers of most large galaxies, including our own Milky Way. The black hole at the center of the Milky Way, known as Sagittarius A star, has a mass of about 4 million solar masses. How supermassive black holes form is still an area of active research. They may grow from stellar mass seeds through prolonged accretion and mergers, or they may form from more exotic processes in the early universe. The report lists each type with typical mass ranges, formation scenarios, and known examples, cross-referencing observational catalogues. When matter falls toward a black hole, it rarely falls straight in. Most matter has some angular momentum, some sideways motion, and this causes it to orbit rather than plunge directly. The result is an accretion disk, a rotating structure of gas and dust spiraling slowly inward. The governing principle is conservation of angular momentum. For a particle to move closer to the black hole, it must lose angular momentum, and this happens through friction and magnetic interactions in the disk. As particles rub against each other and magnetic fields transfer momentum, angular momentum is carried outward through the disk, allowing matter to drift inward. This process heats the disk to high temperatures, and the hot gas radiates energy across the electromagnetic spectrum, from radio waves to X-rays. In the life cycle report, accretion episodes are logged as inflow events, with entries for the accretion rate, how much mass per year is falling in, and the luminosity, the power radiated by the disk. Some black holes accrete at rates approaching the Eddington limit, the point at which radiation pressure from the emitted light pushes back on the infalling gas hard enough to balance gravity, effectively choking off further rapid accretion. Near some accreting black holes, magnetic fields anchored in the disk and twisted by the rotation of the disk, and the black hole itself can launch narrow, relativistic jets perpendicular to the disk. These jets are streams of plasma accelerated to speeds close to the speed of light, and they can extend for thousands or even millions of light years into space. The underlying physics involves magnetohydrodynamics, the equations that describe how charged fluids and magnetic fields interact. Moving plasma can carry magnetic field lines with it, and twisting field lines can exert forces that accelerate particles. The details are complex, requiring numerical simulations to capture the full behavior, but the qualitative picture is clear. The black hole and its disk act as a kind of engine, converting gravitational energy and rotational energy into kinetic energy of the jets. In the life cycle file, jets are listed as feedback channels, mechanisms that return some of the energy harvested from the accretion process back into the surrounding galaxy. These jets can heat gas in the galactic halo, suppress star formation, and influence the large-scale structure of galaxy clusters. Black holes can also interact with each other, and when two black holes orbit each other closely, they emit gravitational waves. Gravitational waves are ripples in the fabric of space-time itself, predicted by Einstein's general relativity, and first directly detected in 2015 by the LIGO observatories. As two black holes spiral inward toward a merger, they lose energy and angular momentum to these waves. The orbit shrinks, the black holes move faster, and the gravitational waves become more intense and higher in frequency. Eventually, the black holes collide and merge into a single, more massive black hole. The waveform of the gravitational wave signal encodes information about the masses and spins of the two original black holes and the properties of the remnant. Numerical relativity, the computational solution of Einstein's equations on supercomputers, provides detailed predictions for these waveforms, and observations match those predictions with remarkable precision. In the life cycle report, each merger is recorded as a line, binary and spiral, gravitational wave emission logged, remnant mass and spin parameters updated. The gravitational waves themselves serve as nature's notification system, carrying news of the merger across the universe to distant observers equipped with sensitive detectors. Even a black hole in isolation is not entirely inert. Quantum field theory predicts that black holes emit a faint thermal radiation, known as Hawking radiation, after Stephen Hawking, who derived this result in the 1970s. The calculation is subtle, but a simplified picture involves quantum fluctuations near the event horizon. In quantum field theory, what we think of as empty space is actually filled with fluctuating fields that can be described as virtual particle-antiparticle pairs briefly appearing and annihilating. Near the event horizon, the extreme curvature of spacetime can cause one member of such a pair to fall into the black hole, while the other escapes to infinity. The escaping particle carries energy away, and to conserve energy, the black hole must lose a tiny amount of mass. This picture is a metaphor for a more rigorous calculation involving quantum fields in curved space-time, but the conclusion is solid. Black holes radiate, and this radiation has a thermal spectrum with a temperature inversely proportional to the black hole's mass. The power output, the rate at which energy is radiated, goes as the inverse square of the mass. Smaller black holes are hotter and radiate more power, larger black holes are colder and dimmer. In the ledger, Hawking radiation appears as a slow leak in the mass column. Mass decreases at a rate inversely proportional to mass squared, with small black holes evaporating faster than large ones. The timescales involved are staggering. The evaporation timescales as the cube of the mass, so even a stellar mass black hole with a few times the Sun's mass would take far longer than the current age of the universe to evaporate completely. A black hole with the mass of the Sun would have an evaporation time on the order of 10 to the power of 67 years, a number so large that it is hard to comprehend. Supermassive black holes with millions or billions of solar masses would persist for times on the order of 10 to the power of 100 years, an era when the universe is unimaginably cold and dark, long after all the stars have exhausted their fuel and faded away. The life cycle report includes a field for expected end of life, and for black holes, this field is filled with numbers best described qualitatively rather than precisely. After nearly all stars have faded, when the universe is cold and dark, when protons themselves may have decayed if certain theories are correct, black holes will still be evaporating, the last embers of matter slowly giving up their energy to the void. As a black hole evaporates, it gets smaller and hotter. The temperature increases, the radiation intensifies, and the final stages of evaporation are predicted to be explosive, though no one has ever observed this because no black holes have had time to reach that stage since the Big Bang. The final moments would release a burst of high-energy particles and radiation, a last gasp before the black hole vanishes entirely, leaving behind only the radiation it emitted. Some theoretical proposals suggest that the evaporation might leave behind a remnant, a tiny stable object with Planck-scale mass, but this is speculative and depends on physics beyond our current confirmed theories. Throughout this entire life cycle, from the initial collapse of the stellar core to the final evaporation eons later, the black hole is governed by a remarkably small set of parameters. The no-hair theorem, a result in general relativity, states that a black hole in equilibrium is completely characterized by just three numbers: its mass, its angular momentum, or spin, and its electric charge. All other details about the matter that fell in, its composition, the arrangement of particles, the history of infell, are erased, hidden behind the event horizon. This simplicity is both elegant and puzzling. It raises deep questions about information and entropy, leading to paradoxes like the black hole information problem, where the apparent loss of information during black hole evaporation seems to conflict with fundamental principles of quantum mechanics. Physicists continue to debate and explore these issues, searching for a framework that consistently describes black holes within a fully quantum theory of gravity. The information paradox deserves its own section in the report, marked with brackets and cross-references to ongoing research papers. The problem arises from a clash between general relativity and quantum mechanics. According to general relativity, anything that crosses the event horizon is lost to the outside universe forever. The information about what fell in, the precise quantum state of every particle, the configuration of every field, seems to vanish. But quantum mechanics insist that information cannot be destroyed. A quantum process must be reversible in principle. Knowing the final state should allow you, at least theoretically, to reconstruct the initial state. Hawking radiation complicates this picture because it appears to be thermal, meaning it carries no information about what fell into the black hole. If a black hole forms, swallows some matter with a specific quantum state, and then evaporates into featureless thermal radiation, where did the information go? This is the paradox. Several proposals attempt to resolve it. One idea is that information is somehow encoded in subtle correlations in the Hawking radiation, correlations that are invisible in a semi-classical approximation, but become apparent when you account for quantum effects more carefully. Another proposal involves modifications to the structure of space-time near the horizon, perhaps involving fuzzy quantum geometry or firewalls, regions of intense energy that destroy infalling information before it can reach the singularity. Holographic principles, inspired by string theory, suggest that the information is never truly inside the black hole, but is instead encoded on the event horizon itself, much like a hologram encodes three-dimensional information on a two-dimensional surface. Each of these ideas has its own challenges and ongoing debates, and the report simply notes that this remains an open question, a gap in our understanding where general relativity and quantum mechanics have not yet been fully reconciled. Rotating black holes add another layer of complexity to the life cycle file. Most astrophysical black holes are expected to have some angular momentum, inherited from the rotation of the collapsing core or acquired through the accretion of matter with net angular momentum. A rotating black hole is described not by the simple Schwarzschild solution, but by the Kerr solution, named after Roy Kerr, who discovered it in the 1960s. The Kerr metric introduces a second parameter, the angular momentum, and the structure near the black hole becomes more intricate. Instead of a single event horizon, there is also an outer boundary called the ergosphere, a region where space-time itself is dragged around by the black hole's rotation. Inside the ergosphere, nothing can remain stationary. Everything is forced to co-rotate with the black hole, at least to some degree. The event horizon for a rotating black hole is smaller than the Schwarzschild radius for the same mass, and the difference depends on how fast the black hole is spinning. A maximally rotating black hole, spinning at the theoretical upper limit, has an event horizon that is half the Schwarzschild radius. The rotation of a black hole has observable consequences. The dragging of spacetime, called frame dragging, or the lens-thirring effect, affects the orbits of nearby matter. Accretion disks around rotating black holes can be torqued and twisted by this effect, and the inner edge of the disk can extend closer to the event horizon for a rotating black hole than for a non-rotating one. This affects the spectrum of the emitted radiation, and astronomers can use these spectral signatures to measure the spin of black holes. High-resolution observations of the accretion flow near Sagittarius A star and other supermassive black holes provide estimates of their spin parameters, and the data suggest that many supermassive black holes are indeed rotating at a significant fraction of the maximum spin. The ergosphere also enables a curious energy extraction mechanism known as the Penrose process. In principle, a particle falling into the ergosphere can split into two, with one fragment falling into the black hole and the other escaping to infinity with more energy than the original particle had. The extra energy comes from the rotational energy of the black hole, which decreases slightly as a result. This process has never been observed directly, but it represents a fundamental prediction of general relativity in the Kerr spacetime. A related mechanism, the Blanford-Znajek process, involves magnetic fields threading the ergosphere and the event horizon. The rotation of the black hole and the magnetic field together can drive a powerful electromagnetic wind, extracting rotational energy and launching jets. This is thought to be the primary engine behind the jets observed in active galactic nuclei and quasars. The life cycle file includes a subsection on energy extraction mechanisms, noting that a rotating black hole can lose both mass and angular momentum over time through these processes, gradually spinning down toward a non-rotating state. Charged black holes are another theoretical possibility, described by the Reissner-Nordström solution for non-rotating charged holes, or the Kerr-Newman solution for rotating charged holes. In principle, a black hole could have a net electric charge if it accreted more matter of one charge than the other. However, astrophysical black holes are expected to have negligible charge. The reason is simple. Space is filled with charged particles, both positive and negative, and any significant charge on a black hole would quickly attract particles of the opposite charge, neutralizing it. The timescale for neutralization is extremely short compared to the other processes in the black hole's life, so the report includes a note that for practical purposes, astrophysical black holes can be treated as electrically neutral. Charged black holes remain interesting theoretically, particularly in the study of black hole thermodynamics and the structure of space-time, but they are not expected to be common in the universe. Black holes also have a thermodynamic description, a framework that connects their properties to concepts like temperature, entropy, and the laws of thermodynamics. Jacob Bekenstein and Stephen Hawking developed this framework in the 1970s, and it remains one of the most profound insights in theoretical physics. The key result is that a black hole has an entropy proportional to the area of its event horizon, not its volume. For a Schwarzschild black hole, the entropy is given by the area in Planck units, divided by 4. This is enormous. A black hole with the mass of the Sun has an entropy vastly larger than any comparable object made of ordinary matter. The temperature of the black hole, as derived by Hawking, is inversely proportional to its mass. Larger black holes are colder, smaller black holes are hotter. These thermodynamic properties satisfy analogues of the usual laws of thermodynamics, with the event horizon area playing the role of entropy and the surface gravity at the horizon playing the role of temperature. The connection between black holes and thermodynamics suggests that black holes are not just gravitational objects but also have deep connections to information theory and quantum mechanics. The entropy of a black hole can be interpreted as a measure of the information hidden behind the event horizon, the number of microscopic states that are consistent with the macroscopic properties we observe. This holographic interpretation, where the maximum information content of a region is proportional to the area of its boundary rather than its volume, has inspired the holographic principle, a conjecture that the universe itself might be describable in terms of information encoded on a distant boundary. The report includes a sidebar on these ideas, noting that they represent a frontier where general relativity, quantum mechanics, and information theory intersect, with implications that reach far beyond black holes themselves. Observations of black holes have advanced dramatically in recent decades. X-ray telescopes have detected emissions from accretion disks around stellar mass black holes in binary systems, where a black hole is pulling matter from a companion star. The flickering and variability of the X-ray light provide clues about the conditions near the event horizon, and careful timing studies reveal the signatures of matter spiraling inward, sometimes at a significant fraction of the speed of light. Supermassive black holes in the centers of galaxies reveal themselves through their influence on nearby stars and gas. Astronomers can track the orbits of stars around Sagittarius A star with exquisite precision, and these orbits follow the paths predicted by general relativity for motion in the gravitational field of a 4 million solar mass object concentrated in a tiny volume. The orbits are so precise that they rule out alternative explanations. The central object must be a black hole. The Event Horizon Telescope collaboration took black hole observations to a new level in 2019 by imaging the shadow of the supermassive black hole in the center of the galaxy Messier 87. The image shows a bright ring of emission surrounding a dark central region, the shadow cast by the event horizon against the backdrop of the glowing accretion disk. The size and shape of the shadow match predictions from general relativity, providing a direct visual confirmation that these objects behave as the theory describes. Subsequent images of Sagittarius A star have further confirmed these results. The report includes a section on observational techniques, noting the challenges of resolving such small angular scales and the sophisticated data processing required to reconstruct images from a network of radio telescopes spread across the Earth. Gravitational wave detectors have opened another window onto black holes, revealing populations that were previously hidden. LIGO, Virgo, and other detectors have detected dozens of black hole mergers, with masses ranging from a few solar masses to nearly 100. The distribution of masses provides clues about how black holes form and evolve. Some of the observed black holes fall into a range that was unexpected, heavier than typical stellar mass black holes, but lighter than supermassive ones, possibly filling in the intermediate mass category. The spins of merging black holes also tell a story. Some mergers involve black holes with aligned spins, suggesting they form together in a binary system. Others have misaligned spins, hinting at dynamical capture in dense stellar environments. Each detection adds a new entry to the catalogue, expanding our census of black holes and refining our models of their formation and evolution. The life cycle report must also consider the environment around a black hole, the ways in which it interacts with and influences its surroundings. A black hole in the center of a galaxy is not isolated. It sits in a dense stellar environment surrounded by gas, dust, and stars. The black hole's gravity dominates the central region, creating a steep potential well into which matter can fall. As matter accretes, the energy released can outshine the entire galaxy, creating a quasar or active galactic nucleus. These objects were far more common in the early universe when galaxies were forming and merging, and gas was more abundant. Today, most supermassive black holes are quiescent, accreting only slowly if at all, but they remain a dominant presence in galactic centers. The feedback from black hole activity, through jets and winds driven by accretion, can regulate star formation in the surrounding galaxy, heating gas and preventing it from collapsing to form new stars. This feedback is thought to play a crucial role in shaping the properties of galaxies, linking the growth of black holes to the evolution of their host galaxies in a process known as co-evolution. In dense stellar environments like globular clusters or the centers of galaxies, black holes can interact directly with stars. A star passing too close to a black hole can be torn apart by tidal forces in a tidal disruption event. The star is stretched into a long stream of gas, part of which falls into the black hole while the rest is flung outward. The infalling gas heats up and emits a bright flare of radiation, visible across vast distances. These events are relatively rare, perhaps one per galaxy every 10,000 to 100,000 years, but when they occur, they provide a dramatic demonstration of the black hole's presence and allow astronomers to study the physics of extreme tidal forces. The life cycle report includes a log of tidal disruption events, each one marked with the mass of the star, the distance at which disruption occurred, and the energy released in the flare. Black holes can also capture smaller compact objects like neutron stars or other black holes. When a neutron star is captured by a black hole, the resulting spiral and merger produce gravitational waves with a characteristic signature, different from black hole mergers because of the neutron star's internal structure. These neutron star-black hole mergers might also produce electromagnetic counterparts, brief bursts of light or gamma rays, if the neutron star is tidally disrupted before crossing the event horizon. Observing both gravitational waves and light from the same event would provide a wealth of information about both the black hole and the neutron star, testing general relativity in new regimes and probing the properties of matter at nuclear densities. Looking further into the distant future, the life cycle report must consider the ultimate fate of black holes in an expanding universe. Current cosmological observations indicate that the universe's expansion is accelerating, driven by dark energy. If this acceleration continues, the universe will become increasingly cold and empty. Stars will exhaust their fuel and fade, galaxies will drift apart beyond each other's horizons, and eventually even protons may decay if certain grand unified theories are correct. In this far future, black holes will be among the last surviving structures, slowly evaporating through Hawking radiation. The universe will be dominated by dilute radiation, remnants of decayed particles, and the faint glow of evaporating black holes. The timescales involved are almost incomprehensible. Stellar mass black holes will evaporate on timescales of 10 to the 67th power years or more. Supermassive black holes will persist for 10 to the 100th power years or longer. These numbers are so large that they make the current age of the universe, about 14 billion years, seem like an instant. In the final stages of a black hole's evaporation, as its mass shrinks to tiny values, the Hawking radiation becomes increasingly intense. The black hole's temperature skyrockets, and the emission shifts to higher and higher energies. The final moments, when the black hole's mass drops below a certain threshold, are predicted to be explosive, a burst of particles and radiation carrying away the last remnants of the black hole's mass energy. This final burst would be a brilliant flash in an otherwise dark and empty universe, a last echo of the matter that once formed a star collapsed into a black hole and slowly evaporated over eons. The report includes speculative notes on this final phase, acknowledging that the details depend on physics we do not yet fully understand. Quantum gravity effects, which are negligible for large black holes, become dominant when the black hole shrinks to near the Planck scale, and our current theories do not provide a clear prediction for what happens in that regime. Throughout this entire narrative, from the fusion, reactions in a massive star's core to the final evaporation in an inconceivably distant future, the black hole remains a natural object, governed by physical laws. It is extreme, certainly, pushing those laws to their limits and revealing gaps in our understanding where quantum mechanics and gravity have not yet been unified. But it is not mysterious in the sense of being unknowable or magical. It follows rules we have written down and tested. The equations of stellar evolution predict when a star will collapse. The equations of general relativity describe the structure of space-time around the resulting black hole. The equations of quantum field theory predict the slow evaporation through Hawking radiation. Each piece fits into a larger framework, a framework that is still incomplete, but that has proven remarkably successful at describing the universe we observe. The story of a black hole, then, is not one of cosmic horror or malevolent forces. It is a story of physical law playing out under extreme conditions, a sequence of transitions from one well-defined state to another. A massive star burns through its fuel, building an iron core that cannot support itself. The core collapses past the point where electron degeneracy pressure can hold it up, and if massive enough, past the point where neutron degeneracy can hold it up. The collapse creates an event horizon, a one-way boundary defined by a simple formula relating mass to radius. The black hole settles into a configuration described by a few parameters, influencing its surroundings through gravity, occasionally accreting matter from a disk, sometimes merging with another black hole and announcing the event with gravitational waves, and all the while slowly, almost imperceptibly, leaking energy through Hawking radiation. The equations that describe each stage are written down, tested against observations, and refined. There are still gaps in our understanding, especially where quantum mechanics and gravity meet, but those gaps are marked clearly in the margins of the report as areas for future research. Imagine this report as a thick file in the universe's archive, one among countless others documenting the life cycles of stars, planets, galaxies, and other objects. The black hole's file begins with a record of the progenitor star, mass, composition, age, and the stages of fusion it underwent. It includes a timestamp for the supernova, notes on the ejected material and the energy released, and an initial mass estimate for the remnant. Subsequent pages log changes in mass due to accretion, with dates and inflow rates recorded in precise units. If the black hole merges with another, there is an entry for the merger, including the gravitational wave signal parameters, the masses of the two objects before the merger, and the mass and spin of the remnant afterward. Further pages track the slow decline of mass due to Hawking radiation, with projected curves extending far into the future, the lines on the graph sloping gently downward over timescales that dwarf not just human history, but the current age of the universe itself. There is a certain peacefulness to viewing black holes this way, as natural outcomes of stellar evolution rather than as entities to be feared. They are extremes, certainly places where gravity is so strong that our everyday intuitions fail, and where the fabric of space-time is bent into shapes we can only describe with advanced mathematics. But they follow rules, the same rules that govern the orbits of planets and the fall of apples. The mystery lies not in the black holes themselves, but in the limits of our current theories, the points where the equations break down and we must wait for new insights to fill in the blanks. As the listener falls asleep, they can imagine this file slowly accumulating pages. Entries are added as the black hole accretes a star that wanders too close, the mass ticking upward by a fraction of a solar mass, the event horizon radius adjusting accordingly. Another entry is added when a merger occurs, the file cross-referenced with the report for the companion black hole, both files now closed and replaced by a new file for the merged remnant. Decades pass, centuries, millennia, eons. The entries for Hawking radiation accumulate, tiny decrements in mass logged at intervals so long that no human-scale observer could notice the change. The universe around the black hole evolves. Stars form and die. Galaxies collide and merge. The cosmic expansion carries distant galaxies beyond the horizon of observation. The black hole remains, a quiet presence in the cosmic ledger, its file growing thicker but its evolution proceeding according to plan. Eventually, in an era so far in the future that it is difficult to conceive, the black hole will have evaporated almost entirely. The final pages of the report describe the last moments. The mass shrinking below a solar mass, then below the mass of a planet, then a mountain, then a speck of dust. The temperature of the Hawking radiation climbs higher and higher, the emission becoming more intense, until in a final flicker, the black hole radiates away its last bit of mass and vanishes. The file is stamped with a closure date, an unimaginably large number of years after the Big Bang, and filed away in the archive. One more life cycle complete, one more object accounted for from birth to fade. This is the story of a black hole, born from the collapse of a massive star whose fusion algorithms reached a dead end at iron, defined by a simple radius formula, quietly influencing its surroundings through gravity, accretion, jets, and mergers, and finally losing mass via Hawking radiation until it fades away into the darkness of a universe grown old and cold. There are still missing pieces, questions about the singularity, the full theory of quantum gravity, the resolution of information paradoxes. Those are marked as pending research, notes in the margins, waiting for future physicists to fill in. But the main story is clear, documented in equations that have been checked and rechecked, observed in the light from accretion disks and the ripples of gravitational waves. It is a story not of monsters but of matter and energy following the rules of the universe, a bureaucratic life cycle report in the greatest archive of all, stamped with a simple label: black hole, birth recorded, interactions logged, evaporation scheduled on timescales too long for any witness to remain. The next story is about to begin. Please relax and enjoy. Tonight we're not watching galaxies crash in slow-motion animations or dramatic cosmic collisions rendered in brilliant false colour. Instead, we're opening a quiet merger file in the local group's imaginary office, a beige folder with worn edges, tucked between other routine cases in a filing cabinet that spans several billion light-years. Inside this folder, 2 spiral galaxies have a meeting scheduled, penciled in for approximately 4 billion years from now, give or take a few hundred million. There's no urgency here, no flashing red lights or countdown clocks, just paperwork, measurements, and projections logged with the same calm precision you'd find in any long-term planning document. The Milky Way and Andromeda are simply 2 spiral galaxies sharing a neighbourhood. They're part of what astronomers call the local group, a small collection of gravitationally bound galaxies that includes these 2 giants along with a few dozen smaller companions scattered throughout a region roughly 10 million light-years across. In the grand scheme of the universe, this is a quiet corner, a suburban cul-de-sac where things move slowly and predictably. Andromeda's approach toward us isn't an emergency or a crisis waiting to happen. It's just an appointment that's been on the books since these galaxies first formed, written in the language of gravity and motion that governs everything in the cosmos. Our task tonight is to flip through the pages of Andromeda's file, examining what it is, how we measured it, and what its long-term plans look like. Think of it as reviewing a neighbour's moving schedule, except the neighbour is moving at a few hundred kilometres per second, and the move itself will take several billion years to complete. Every measurement, every observation, every simulation is just another page added to this growing dossier, building a comprehensive picture of an event that's both inevitable and impossibly distant. Let's start with the basics, the cover sheet of Andromeda's file. Its formal designation is M31 or NGC 224, but most people just call it Andromeda, named after the constellation where it appears in Earth's night sky. From a dark location, far from city lights, you can see it with your naked eye as a faint, elongated smudge. A pale oval glow that doesn't look like much until you realise you're seeing the combined light of hundreds of billions of stars located roughly 2.5 million light-years away. That's the current best estimate of its distance, refined over decades of increasingly precise measurements. 2.5 million light-years means that the light entering your eye tonight left Andromeda when early human ancestors were just beginning to use stone tools on Earth. Andromeda holds the status of the Milky Way's nearest giant neighbour, and the largest member of the local group. In the file, this appears as a simple cover sheet with basic information. Coordinates in the sky at right ascension 1 hour, declination, 41 degrees north, estimated distance of approximately 2.5 million light-years, overall mass somewhere around 1 trillion solar masses when you include all the dark matter, and a short note at the bottom that reads spiral, roughly similar class to Milky Way, currently inbound. The spiral classification means it has a flattened rotating disk with prominent spiral arms, a central bulge, and an extended spherical halo. It's designated as an SB or SBC spiral, indicating moderately wound arms and a fairly substantial central bulge relative to its disk. Turn the page and you'll find the stellar census, a long detailed inventory of Andromeda's residents. The galaxy contains somewhere between 800 billion and 1 trillion stars, though the exact count is fuzzy because faint, low-mass stars are hard to detect at that distance, and the outer reaches of the galaxy fade into an uncertain boundary, where it's difficult to say precisely where Andromeda ends and intergalactic space begins. These stars aren't distributed uniformly. The central bulge holds a dense concentration of mostly older, redder stars, objects that formed billions of years ago when the galaxy was young. Their orbits are random, not organised into any particular pattern, giving the bulge a roughly spherical or slightly football-shaped appearance. The disk is where you find the spiral structure, traced by lanes of young blue stars, glowing gas clouds, and dark dust that absorbs background light. The spiral arms aren't solid structures but density waves, regions where stars and gas pile up temporarily as they orbit around the galaxy's centre, like cars bunching up in slower lanes of traffic. Stars form in these dense regions, live their brief bright lives, and then drift away as their orbits carry them forward. The youngest, most massive stars don't live long enough to leave the spiral arms, so they trace the pattern brightly while older stars fill in the spaces between. Andromeda's disk extends roughly 200,000 light-years from edge to edge, making it somewhat larger than the Milky Way's disk, though comparisons depend on exactly where you decide each galaxy's edge actually is. Beyond the bright disk lies the stellar halo, a sparse spherical distribution of old stars and ancient globular clusters. These objects formed early in the galaxy's history and now orbit in elongated elliptical paths that carry them far above and below the disk plane. The halo doesn't contribute much light. If you were to visit Andromeda, you'd hardly notice it compared to the brilliant disk, but it contains important clues about the galaxy's formation history. Many halo stars show unusual chemical compositions or orbit in coherent streams, suggesting they were once part of smaller satellite galaxies that Andromeda consumed long ago. In the merger paperwork, this is the resident list, a long detailed census noting how many stars Andromeda brings to the future meeting, organised by age, mass, location and orbital characteristics, without dramatising any of them. Another section of the file catalogues the interstellar medium, the material between the stars. Dark dust lanes trace Andromeda's spiral arms in optical photographs visible as brown streaks that block light from background stars. This dust is made of tiny solid particles, mostly carbon and silicate compounds that formed in the atmospheres of dying stars and were ejected into space. Mixed with the dust are vast clouds of gas, mostly hydrogen with smaller amounts of helium and trace quantities of heavier elements. Some of this gas is cold and neutral, detectable by radio telescopes tuned to the 21 centimeter wavelength where hydrogen atoms naturally emit. Other regions are warmer and ionized, glowing in the red light of hydrogen alpha emission, where the energetic radiation from young stars strips electrons from nearby atoms. Different wavelengths reveal different components of this interstellar inventory. Optical images highlight the dust lanes and the bright young stars that illuminate them. Radio maps trace vast reservoirs of neutral hydrogen, extending beyond the visible disk, showing how much raw material Andromeda has available for future star formation. Infrared observations penetrate the dust, revealing cooler stars and highlighting regions where dust clouds warmed by nearby stars glow in thermal emission. Ultraviolet light from satellites traces the hottest young stars and the regions of active star formation they inhabit. In the file, this is the Interstellar Medium folder, listing available gas and dust inventories like warehouse stock. So many solar masses of cold hydrogen here, so many solar masses of molecular gas there, dust-to-gas ratios in various regions, and star-forming rates measured in solar masses per year. These are the raw materials that will be shuffled, compressed, and rearranged during the merger. Clipped to the main Andromeda file are smaller subfolders documenting its satellite galaxies. The two largest and most obvious are M32 and M110, visible as small, fuzzy blobs near Andromeda in photographs. M32 is a compact elliptical galaxy, dense and devoid of gas and dust, containing mostly older stars in a small volume. Its proximity to Andromeda's disk suggests a close gravitational relationship, and some simulations suggest it may have once been larger, before tidal forces from Andromeda stripped away its outer stars. M110 is a dwarf elliptical, larger and more diffuse than M32, also containing primarily old stars but with some evidence of past star formation episodes. Beyond these obvious companions, astronomers have identified dozens of smaller dwarf spheroidal and dwarf irregular galaxies orbiting Andromeda at various distances. Many of these satellites are extremely faint, containing only thousands or millions of stars rather than billions, and require large telescopes and careful surveys to detect. Each satellite has its own subfolder notation, mass, distance from Andromeda, orbital properties if known, stellar populations, and a note about its likely fate. Some satellites are compact and may survive the merger as distinct objects orbiting the combined remnant. Others show signs of tidal disruption, streams of stars being pulled away by Andromeda's gravity, and will likely be completely absorbed over time. In our calm framing, they are simply associated systems, with lines on diagrams indicating their current orbits and their relationship to the primary galaxy. The file gains thickness as we add pages documenting how Andromeda entered the historical record. For most of human history, it was visible as a fuzzy patch of light, noted by various cultures, but not understood as anything more than a nebula, a cloud of glowing gas somewhere in the sky among the stars. Persian astronomers recorded it in the 10th century. Charles Messier included it as the 31st entry in his catalogue of objects that might be confused with comets. William Herschel, building ever larger telescopes in the late 18th and early 19th centuries, could resolve individual bright regions within it, but couldn't determine its true nature or distance. The breakthrough came in the 1920s when Edwin Hubble used the newly completed 100-inch telescope at Mount Wilson to identify Cepheid variable stars in Andromeda. Cepheid variables are stars that pulse regularly in brightness over periods of days to weeks, and crucially, their pulsation period is directly related to their intrinsic luminosity. If you know how bright a Cepheid truly is, and you can measure how bright it appears from Earth, you can calculate its distance using the inverse square law of light. Hubble's Cepheids in Andromeda turned out to be extremely faint despite being intrinsically very bright stars, which meant they had to be extremely far away, far beyond any distance that would place them within the Milky Way. This observation earned Andromeda a big stamp in the file: confirmed external galaxy. What had been suspected or debated was now documented fact. The universe contained multiple galaxies, separate island universes of stars, each comparable to or larger than the Milky Way itself. The cosmic scale suddenly expanded enormously. Distances that had been uncertain or debated were now written more precisely in the log. Early distance estimates put Andromeda at around 900,000 light-years away, though later refinements of the Cepheid period luminosity relationship and recognition of different types of Cepheids eventually pushed the distance out to the currently accepted value of about 2.5 million light-years. The distance measurement section of the file contains multiple entries, each representing different methods astronomers have used to cross-check and refine Andromeda's position. Cepheid variables remain a primary tool, but they're not the only one. Red giant branch stars provide another standard candle. These are elderly stars in a specific evolutionary phase, and the tip of the red giant branch, the brightest point these stars reach before moving on to other phases, occurs at a known luminosity. By identifying red giant branch stars in Andromeda and measuring their apparent brightness, astronomers can calculate distance independently of the Cepheid method. Other techniques involve planetary nebulae, the glowing shells of gas ejected by dying stars, which have characteristic luminosities. There are also methods based on the properties of globular clusters, the brightnesses of certain types of supernovae, and careful modelling of the galaxy's rotation curve combined with its angular size on the sky. In the paperwork metaphor, these methods are different rulers that all point to roughly the same number, turning a fuzzy estimate into a well-documented entry in the distance column. The convergence of multiple independent methods gives astronomers confidence that the value is correct within perhaps 5 or 10%. Not perfect precision, but good enough for most purposes. Another critical measurement appears in the motion section of the file: radial velocity, the speed at which Andromeda is moving toward or away from us along our line of sight. This comes from spectroscopy, the technique of splitting light into its component wavelengths to reveal the detailed pattern of bright and dark lines created by various elements in a star's atmosphere. When a star or galaxy moves toward or away from us, the Doppler effect shifts these spectral lines towards shorter or longer wavelengths respectively, just as the pitch of a siren changes as an ambulance passes by. Andromeda's spectrum shows a slight blue shift, meaning its light is compressed toward shorter wavelengths, indicating motion toward the Milky Way. The measured radial velocity is about 300 km per second inbound, though this number needs to be corrected for the Sun's motion around the Milky Way's centre and the Milky Way's own motion through the local group. After accounting for these corrections, Andromeda is approaching at roughly 100 to 120 km per second relative to the Milky Way's centre of mass. In the merger file, this appears as a simple line in the motion section, approaching at approximately 110 km per second, with a small arrow pointing inward on a chart showing the local group. For a long time, that inward arrow was all astronomers had. Radial velocity is relatively easy to measure because the Doppler shift of spectral lines can be detected with high precision. But galaxies also move sideways across the sky, perpendicular to our line of sight, and this proper motion is much harder to measure. Andromeda is so far away that even moving at hundreds of kilometers per second, its position on the sky shifts by only a tiny fraction of an arcsecond per year. Detecting such minute motions requires observing the same stars repeatedly over many years with extremely accurate position measurements. The Hubble Space Telescope made this possible through patient, careful work. By observing individual stars in Andromeda's halo over multiple years and tracking their positions relative to distant background galaxies, astronomers could measure the sideways component of Andromeda's motion. The results, published in the early 2000s, showed that Andromeda is moving slightly sideways relative to us, but not by much. The tangential velocity is relatively small compared to the radial velocity, which means Andromeda's path is aimed nearly straight at us, rather than in some more oblique direction. In the ledger, a second arrow gets added to the chart, perpendicular to the first inward-pointing arrow but much shorter. This sideways component is crucial because it determines the exact trajectory of the future encounter. If the tangential velocity were large enough, Andromeda might miss the Milky Way entirely, passing by at some distance and continuing on its way. But the measured proper motion indicates a more direct approach. The two arrows together, inward velocity and small sideways velocity, allow simulations to predict the eventual encounter more accurately. The meeting will happen, not might happen, and it will be close enough that the galaxies won't just fly past each other, but will gravitationally capture each other and eventually merge. Estimating the total masses of the merger partners fills another section of the file with numbers and uncertainties. Mass is difficult to measure directly in astronomy because we can't put galaxies on a scale. Instead, we infer mass from its gravitational effects on visible objects. For Andromeda, this means tracking the orbital velocities of stars at various distances from the galaxy's centre. Stars farther from the centre should move more slowly if most of the galaxy's mass were concentrated in the bright central bulge and disk, following the same rules that govern planetary orbits where outer planets move more slowly than inner ones. But observations show something different. Stars and gas clouds far from Andromeda's centre move faster than expected if only visible matter were present. The rotation curve, a graph showing orbital velocity versus distance from the centre, stays roughly flat far out into the galaxy, rather than declining as it should. This is the signature of dark matter, an invisible component that doesn't emit or absorb light but exerts gravitational force. To explain the observed rotation curve, Andromeda must be embedded in a large halo of dark matter extending far beyond the visible disk. Similar measurements work for the Milky Way. Both galaxies carry these large extended halos of invisible mass, probably made of some exotic particle that interacts only through gravity and hasn't yet been directly detected in laboratory experiments. The numbers show that the total mass of Andromeda, including dark matter, is somewhere around 1 trillion solar masses, while the Milky Way is somewhat less massive, perhaps 700 billion solar masses. These uncertainties are substantial, factors of 2 or more, but they're good enough to populate the total mass field for each galaxy in the paperwork. The masses are important for forecasting how strongly the galaxies will tug on each other as they draw closer, and how quickly their orbits will decay as gravitational interactions drain orbital energy. The dark matter halos themselves deserve a separate notation in the file. These halos are roughly spherical envelopes surrounding each galaxy, extending several 100,000 light-years or more from their centres. Unlike the bright disks, which are relatively compact, the halos overlap and intermingle well before the visible structures come close. The outer reaches of Andromeda's dark matter halo and the Milky Way's dark matter halo are probably already interacting gravitationally at their boundaries. In the file, this appears as a note, outer halos overlapping. It's an important detail because it means the merger process doesn't begin with a sudden collision, but with a gradual increase in gravitational influence. Stars at the edges of each galaxy's halo already feel the pull of the other galaxy, even if only weakly. Over time, this pull grows stronger. The halos respond first, their outer regions beginning to blend and share material, while the bright inner regions remain distinct and separate. The merger timeline doesn't start 4 billion years from now, when the visible disks cross paths. It started long ago when these two galaxies first became gravitationally bound to each other, and it's been proceeding slowly ever since. Computer simulations project the future orbits forward in time, running the gravitational physics through millions of computational time steps. These simulations start with the current positions and velocities of the Milky Way and Andromeda, add reasonable estimates of their mass distributions, and let gravity do the work. The models show a first close passage where the two galaxies swing past each other, their disks coming within perhaps 50,000 light-years. This isn't a head-on collision, but more like a side-swiping pass where the outer parts of each galaxy begin to interact strongly. Gravity is a gentle force at cosmic scales, but it's also relentless. As the galaxies pass, tidal forces stretch them, pulling stars and gas out into long streams and tails. These tidal features can extend for hundreds of thousands of light-years, great arcs of stars and gas drawn out by differential gravitational pull. The inner parts of each galaxy, feeling stronger gravity toward the other galaxy, get pulled forward. The outer parts, feeling weaker gravity, get left behind. The result is elongation and distortion. After the first passage, the galaxies don't simply fly apart. They're gravitationally bound, moving too, slowly to escape each other's pull. Instead, they swing back around for a second encounter, then a third. Each passage brings them closer as tidal interactions and dynamical friction drain orbital energy. Dynamical friction is a subtle effect where each galaxy's wake through the other's dark matter halo creates drag, slowing the relative motion. Think of it like a satellite slowly spiraling down through a thin atmosphere. It's not obvious on any single orbit, but over many orbits the cumulative effect is substantial. The simulations show this orbital decay playing out over billions of years. After perhaps 3 or 4 close passages, separated by hundreds of millions of years each, the galaxies no longer have enough energy to swing apart. They begin to merge in earnest, their disks overlapping, their central regions sinking toward a common center. Instead of 2 distinct galaxies moving past each other, you have one chaotic system with stars and gas moving in a tangle of intersecting orbits. In the merger paperwork, this is the future projections section. Multiple timelines plotted and archived, with predicted encounter times and structural changes logged at each step. The first close passage might occur in about 4 billion years, plus or minus half a billion. Complete merging might take another billion or 2 beyond that. The uncertainties are large because small changes in current velocities or mass estimates produce significant changes in the timeline, but the overall sequence is robust. During these encounters, gravitational interactions compress gas clouds, particularly in regions where gas streams from the two galaxies collide, or where tidal forces pile material up. Compressed gas can cool and fragment, triggering bursts of star formation. This means new stars may form at elevated rates during the merger, particularly during the close passages when tidal effects are strongest. Observations of other merging galaxies elsewhere in the universe show this starburst activity clearly. Regions where thousands of new stars form in dense clusters, their ultraviolet light ionizing surrounding gas and creating brilliant glowing nebulae. In our calm framing, these are simply activity spikes noted in the file. The star formation rate, normally measured in solar masses per year, increases temporarily during merger events. The Milky Way currently forms perhaps 1 to 2 solar masses of new stars per year. Andromeda's rate is somewhat lower. During the merger, these rates might increase by factors of several or more for brief periods. Not every region will experience this. Some areas will have their gas heated and dispersed by shock waves, actually suppressing star formation. But in aggregate, the merger will likely create a generation of new stars, their formation dates logged in the file, with locations and estimated numbers, treated not as explosions for dramatic effect, but as normal consequences of gas dynamics during gravitational interactions. As the galaxies interact, stars get flung onto new orbits. Some will be ejected entirely, thrown clear of the system with enough velocity to escape into intergalactic space. These escaping stars will spend the rest of their existence travelling alone through the void between galaxy clusters, lighting their small volumes of space but disconnected from any larger structure. Most stars, however, remain bound to the merged system but on different orbits than they followed originally. Stars that once circled the Milky Way's centre in neat circular paths might find themselves on elongated elliptical orbits, carrying them far above and below the merged galaxy's eventual disk. Stars from Andromeda's halo might sink inward toward the central regions. The result is a redistribution of the stellar population. The file gains maps showing these tidal streams as redistribution notes. Long arcs and loops of stars orbit through the combined gravitational potential, slowly mixing and blending. Features that were once distinct, Andromeda's disk, the Milky Way's bar, the separate bulges, lose their identities and merge into a more homogeneous structure. Stars originally tagged as Milky Way or Andromeda in the census pages now travel on new paths, their origins impossible to determine from their current positions, but all of them still part of the merged system's ledger. The final remnant, after enough time for the orbits to relax and settle, will be a single more massive galaxy. Simulations suggest this remnant will likely be an elliptical galaxy, or possibly a large lenticular galaxy with a weak disk. Elliptical galaxies are characterized by their rounded or football-shaped appearance and their lack of obvious disk structure. Stars in ellipticals move on random orbits rather than orderly circular paths, giving the galaxy a smooth, featureless appearance, without spiral arms or prominent dust lanes. This makes sense as an outcome because mergers destroy the organized rotation of spiral disks, scrambling the orbits into a more chaotic distribution. The exact properties of the remnant depend on the details of the merger, the mass ratio between the two galaxies, the angle of their collision, how much gas each contained, and how much star formation occurred during the process. Some simulations produce a pure elliptical. Others show a remnant with a small remaining disk of gas and stars that survived the merger, relatively intact, or that formed from gas that settled back down after being stirred up. The merged galaxy will be more massive than either progenitor, combining the stars from both the Milky Way and Andromeda, plus any new stars formed during the merger. Total stellar mass might reach several 100 billion solar masses or more. In the merger paperwork, two separate files are gradually replaced by one combined folder with updated entries. The cover sheet now lists a single galaxy rather than two, with new values, mass of approximately 1 to 1.5 trillion solar masses including dark matter, stellar mass of several 100 billion solar masses, morphological type of elliptical or lenticular, structure notes indicating a smooth light distribution, with possible tidal features still visible in the outer regions, and a tag identifying it as the dominant member of the local group. The old entries for Milky Way and Andromeda are moved to an appendix marked Merged Components, Historical Reference. A small notation appears in a subsection of the file regarding the solar system. Simulations that track individual stars through the merger can follow the Sun's orbit specifically. The results are reassuring in some ways and unsettling in others. Direct stellar collisions are extraordinarily unlikely. Space is mostly empty, and even during a galaxy merger, the typical distance between stars remains enormous compared to the sizes of stars themselves. The chances of another star passing close enough to the Sun to disrupt the planet's orbit significantly are very small. Not zero, but small enough that it probably won't happen. However, the Sun's orbit around the galactic centre will definitely be perturbed. Currently, the Sun orbits roughly 26,000 light-years from the Milky Way's centre in a nearly circular path that takes about 200 million years to complete. During the merger, gravitational interactions with passing stars and with the changing overall gravitational potential of the merged system will alter this orbit. The Sun might be flung outward to a larger orbital radius, ending up in the outer regions of the merged galaxy, or it might be scattered inward toward the central regions, or it might gain enough velocity to escape the merged galaxy entirely and wander through intergalactic space, though this seems less likely. In the file, the solar system is a small sub-entry, easy to overlook among the vast quantities of data about billions of stars. Orbit modified likely remains bound to merged remnant, direct stellar collisions improbable. It's a minor notation in a very large project log. From the perspective of someone cataloguing galaxy mergers, the fate of one particular star system barely rates a footnote. From the perspective of anyone living on Earth, it's the most important detail in the entire file. But in our calm framing tonight, it's just another data point. The Sun will continue shining, the planets will continue orbiting, and life, if any still exists on Earth 4 billion years from now, will experience a change of scenery but not necessarily catastrophe. The night sky will look different. The Sun's neighbours will change. but the solar system itself will likely survive, reassigned to a new neighbourhood in the merged galaxy's organisational chart. The Andromeda-Milky Way merger isn't a special case or a rare event. The file contains reference sections noting that astronomers routinely observe galaxies in various stages of merging throughout the universe. Point a telescope at a random patch of sky and survey it deeply enough, and you'll find pairs of galaxies in close proximity with distorted shapes, bridges of stars and gas connecting them, or tidal tails streaming away from the interaction site. Some show two distinct nuclei embedded in a single shared envelope. Others are further along, blended into single irregular systems with chaotic structures suggesting recent merger activity. Famous examples include the Antennae galaxies, a pair locked in merger about 45 million light-years away, showing spectacular tidal tails and intense star formation in the collision regions. The Mice galaxies display similar features with long thin tails drawn out by tidal forces. ARP 220, an ultraluminous infrared galaxy, appears to be the merger remnant of two gas-rich spirals, now forming stars at prodigious rates as compressed gas collapses in the galaxy's core. These external examples act as reference cases in the Andromeda file. Similar events observed at distances and stages ranging from first contact through final coalescence, confirming that slow, large-scale mergers are standard operations in cosmic structure formation. Galaxy mergers are a natural outcome of cosmic structure formation. In the early universe, small dark matter halos formed first, and galaxies grew within them through mergers and accretion. Over cosmic history, small galaxies merged into larger ones, building up the population of massive galaxies we see today. This process continues, though at a slower pace now than in the distant past when the universe was denser and interactions were more frequent. The Milky Way and Andromeda are simply continuing this process, two products of earlier mergers now scheduled to merge themselves. Looking forward, the local group structure will continue evolving after the Milky Way-Andromeda merger completes. The merged remnant will dominate the group gravitationally, and smaller members will continue orbiting it, or eventually merge with it as well. The Triangulum galaxy, currently the third largest local group member at about 60,000 light-years across, and perhaps 40 billion solar masses, will likely merge with the Andromeda Milky Way remnant eventually, though the timing is uncertain. The various dwarf galaxies scattered through the group will continue their own slow evolution, some merging with the central giant, others perhaps remaining as satellites indefinitely. Over truly long timescales, tens or hundreds of billions of years, the local group will become even more bound together while separating further from other galaxy groups due to the expansion of the universe. The accelerating cosmic expansion driven by dark energy means that regions not already gravitationally bound are moving apart faster and faster, eventually reaching recession velocities exceeding the speed of light. The local group's gravity is strong enough to resist this expansion internally, but external groups will recede beyond our cosmic horizon. Future observers in the merged galaxy, if any exist, will see a much emptier universe than we do, with only the bound members of the local group visible, and most other galaxies having vanished beyond the observable horizon. In our organisational system, all of this is simply a series of updates to the group chart. Who orbits whom, how fast, and in what configuration. The chart gets redrawn periodically as mergers complete and new structures form. Lines connecting member galaxies get erased and redrawn, mass values get updated. The chart becomes simpler over time as separate entries consolidate into fewer, more massive objects. It's long-term planning on a cosmic scale, the kind of slow, bureaucratic reorganization that takes billions of years to finalize, but whose outcome can be projected reasonably well given current data. Nothing about this merger is urgent on human timescales, or even on the timescales of human civilization. 4 billion years is a length of time so vast it defies intuitive understanding. For reference, Earth itself is only about 4.5 billion years old. 4 billion years ago, Earth was newly formed, still cooling from its molten state, and life had not yet appeared. 4 billion years is enough time for complex multicellular life to evolve from nothing, for continents to form and break apart multiple times, for thousands of ice ages to come and go, for entire mountain ranges to rise and erode away to flat plains. Entire evolutionary lineages have appeared, flourished, and gone extinct on shorter timescales. In 4 billion years, the Sun will have brightened substantially as it ages. The gradual increase in solar luminosity means Earth's oceans will likely boil away within 1 billion or 2 years from now, rendering the planet uninhabitable for life as we know it long before the galaxy merger becomes directly relevant. If humanity survives that long, and that's an enormous if, we will have found ways to leave Earth, possibly leave the solar system, and spread across the galaxy. Our distant descendants, if they exist, might witness the merger as inhabitants of multiple star systems scattered through what is now the Milky Way, watching as the night sky gradually transforms over millions of years as Andromeda grows larger and eventually dominates the view. But all of that is speculation layered on speculation. The merger file doesn't concern itself with such contingencies. It simply documents the physics, current positions, velocities, masses, and the gravitational interactions that will unfold over the next several billion years. It's as certain as anything in astronomy can be. The galaxies are approaching, their motions are measured, and the outcome is calculable. The details might vary depending on small factors we haven't measured precisely, but the broad strokes are clear and logged in the file with appropriate confidence intervals. As we close the Andromeda, merge a file and slide it back into the cosmic filing cabinet, the overall impression is one of calm inevitability rather than drama. This isn't a collision in the catastrophic sense. It's not an explosion or a disaster. It's a slow gravitational dance between two large spiral galaxies, playing out over billions of years according to laws of physics that can be calculated and predicted with reasonable accuracy. The stars involved will barely notice on any individual level. A star in Andromeda's disk will eventually find itself orbiting a merged galaxy's centre rather than Andromeda's centre, but from the star's perspective, it's still just a gravitational well to orbit around. The physics doesn't care about the labels. For us, safe in our present moment, the merger is simply an entry in a very long-term schedule. It's a meeting confirmed, penciled into the calendar billions of years ahead. The file is complete enough that we understand what will happen even if we won't be around to see it. The measurements are logged, the velocities are recorded, the simulations have been run multiple times with varying assumptions, all pointing to similar outcomes. In some ways, it's already done. The equations don't care about time direction, and the future state is as determined as the past state, just a matter of solving forward rather than backward. There's something peaceful about that kind of inevitability. Not the inevitability of personal mortality or the heat death of the universe. Those carry emotional weight. But the inevitability of two galaxies slowly spiraling together, following paths carved out by their mutual gravity, is just physics proceeding calmly forward. No one needs to do anything about it. No one can do anything about it. It will happen when it happens, and the universe will continue afterward with one merged galaxy where there were once two. As you drift towards sleep, you can imagine that quiet cosmic office where galaxies have their own folders in a filing cabinet that stretches across the observable universe. Each folder contains careful measurements, projected timelines, and notes about future interactions. Some folders are thick with decades of observations. Others are thin, newly opened for recently discovered systems. The Andromeda file is one of the thicker ones, well studied and frequently referenced because it's close enough to observe in detail and because it happens to involve our own galaxy. The file sits there, marked with a calm bureaucratic note. Future merger with Milky Way, meeting confirmed approximately 4 billion years from now, plus or minus uncertainties. There's no red stamp saying urgent, no flashing indicator demanding immediate attention, just a routine entry in the long, slow process of cosmic structure formation, proceeding as scheduled, documented and filed for future reference by anyone curious enough to pull the folder and flip through its pages. The next story is about to begin, please relax and enjoy. Tonight we're opening a very particular kind of book. It's not a thriller, not an adventure tale, not even really a story in the usual sense. It's more like flipping through an old attendance ledger from a physics classroom, the kind where every object in the universe is signed in with a single number next to its name. That number describes one simple thing: how much that object hates being pushed around. This isn't about rockets launching or cars crashing into walls. Those things happen certainly, but they're just the dramatic consequences of something much quieter, much more fundamental. What we're looking at tonight is inertial mass, the universe's way of keeping track of stubbornness, Every marble, every freight train, every grain of sand has its own entry in this ledger, and that entry tells you how reluctant it is to change whatever it's currently doing. Some numbers are small, some are enormous, but they're all just sitting there on the page waiting to explain why things move the way they do. If you open the ledger to the first page, you'll find a rule written at the very top, underlined twice, in careful handwriting. It's Newton's first law, though it doesn't announce itself with any fanfare. It just says, if nothing pushes or pulls an object, that object keeps doing whatever it was already doing. If it was sitting still, it stays still. If it was moving in a straight line at a constant speed, it continues moving in that same straight line at that same speed, forever, if nothing interferes. This is the default setting. This is what the universe does when left alone. Inertia is simply the name we give to this tendency. The tendency to maintain the status quo. It's not a force. It's not something that makes objects resist forces. It's just the baseline behavior, the entry at the top of every page that says, without an unbalanced force, motion unchanged. It's a profoundly boring rule, and yet it underlies absolutely everything else in the book. Every complicated motion, every collision, every orbit begins with this quiet assumption that things prefer not to change. But of course, things do change. Doors open, cars accelerate, balls curve through the air, something must be pushing or pulling. And when that happens, the ledger opens to its next page, where Newton's second law is written out in a neat column. This is where reluctance becomes a number you can actually use. The equation is simple. Acceleration equals force divided by mass. Or if you prefer to rearrange it, force equals mass times acceleration. The ledger prefers the first version because it makes the relationship clearer. If you apply the same force to two different objects, the one with more mass accelerates less. The one with less mass accelerates more. Mass is the scaling factor, the thing that determines how much motion change you get for your effort. In gentler terms, imagine you have a certain amount of push available. You apply it to a marble and the marble shoots, off quickly, gaining speed in a hurry. You apply the exact same push to a bowling ball and it barely budges, creeping forward at a fraction of the marble's acceleration. Same force, wildly different results. The only difference is the number written in the mass column of the attendance ledger. The marble has a small entry, the bowling ball has a large one, that's all. The universe looks up the mass, divides your force by it, and hands you back an acceleration. This becomes especially clear if you set up a very simple experiment. Picture two identical carts on a smooth track, the kind you might find in a high school physics lab. The track is nearly frictionless, or at least friction is low enough that we can mostly ignore it for a moment. One cart is empty, the other is loaded with sandbags, adding significant mass. Now you push both carts with the same steady force. Maybe you use a spring scale or a weight on a pulley, so the force is consistent and measurable. You let them go. The empty cart speeds up quickly, rolling down the track with obvious acceleration. The heavy cart responds sluggishly, taking its time, gaining speed at a much more leisurely rate. In the attendance ledger, both carts are marked present, but their entries are different. The empty cart is labelled with a small mass, easy to accelerate, quick to respond. The loaded cart has a much larger number next to its name, stubborn, resistant, requiring much more force to achieve the same acceleration. This is inertia made tangible. It's not an abstract concept anymore. It's a measurable, everyday quantity. You can feel it in your hands when you try to push a shopping cart that someone has filled with canned goods versus one that's nearly empty. You can see it in the way a freight train takes miles to stop even after the brakes are applied, while a bicycle comes to a halt in a few meters. Every object has its number, and that number determines how it responds to being pushed. But there's a subtlety here that the ledger needs to clarify, because people often confuse two related but distinct ideas. Mass and weight are not the same thing, even though we use them interchangeably in casual conversation. Mass is an intrinsic property of an object. It measures how much inertia the object has, how much it resists changes in motion. This number doesn't change based on where the object is. A bowling ball has the same mass whether it's on Earth, on the Moon, or floating in deep space far from any gravitational field. The ledger records mass as a fixed entry attached to the object's identity. Weight, on the other hand, is a force. It's the result of gravity acting on that mass. Weight depends on the gravitational field strength at the object's location. On Earth, The bowling ball weighs a certain amount because Earth's gravity is pulling on its mass with a specific force. On the Moon, where gravity is weaker, the same bowling ball weighs much less, about 1/6 as much. Its mass hasn't changed. The ledger's mass column still shows the same number, but the weight column, which depends on the local gravitational acceleration, shows a different value. This distinction is written carefully in the margins of the ledger. Same object, same mass everywhere, different weights depending on location. It's an important note because it prevents confusion when we start talking about how objects fall and how gravity interacts with them. Which brings us to another number in the ledger, one that at first seems like it should be separate but turns out to be mysteriously identical. This is gravitational mass. Gravitational mass measures how strongly gravity acts on an object and how strongly that object attracts other masses. When you calculate the gravitational force between two objects using Newton's law of gravitation, the masses that appear in that equation are gravitational masses. They tell you how much each object participates in the gravitational interaction. So now the ledger appears to have two columns for each object, one for inertial mass, which describes how hard it is to accelerate that object, and one for gravitational mass, which describes how strongly gravity pulls on it and how strongly it pulls back on other things. These seem like they should be different properties. Resistance to acceleration and participation in gravity don't obviously have anything to do with each other, and yet, as far as anyone has ever been able to measure, these two numbers are always exactly the same. For every object ever tested, inertial mass equals gravitational mass to within the limits of experimental precision. The ledger is filled with entries that show this equality over and over again. Inertial mass equals gravitational mass. No discrepancy detected. It's as if the universe keeps insisting on the same answer, no matter how many times we check. This equality shows up in some very simple and elegant experiments. Consider dropping two objects of different masses in a vacuum chamber, so air resistance doesn't interfere. A feather and a hammer, for example, if you're on the Moon where there's no atmosphere. Both objects fall with exactly the same acceleration. They hit the ground at the same time. Why? Because the gravitational force on an object is proportional to its gravitational mass, but the acceleration that force produces is inversely proportional to its inertial mass. If gravitational mass and inertial mass are the same, these two effects cancel perfectly. The force is bigger on a heavier object, but it's also harder to accelerate a heavier object by exactly the same factor. The result? Same acceleration for everything, regardless of mass. Or consider pendulums. A pendulum's period, the time it takes to complete one full swing, depends on its length and the local gravitational acceleration, but not on its mass, as long as inertial and gravitational mass are equal. You can hang two pendulums of the same length, one made of lead and one made of aluminum, and they'll swing in perfect unison. The ledger notes this carefully. Different materials, different masses, but the ratio of gravitational to inertial mass is the same for both, so the period is identical. These aren't just classroom demonstrations, they're precision tests of a fundamental assumption, and the assumption keeps holding up test after test, decade after decade. This strange equality became even more interesting when Einstein started thinking seriously about it. He imagined a person standing inside a sealed elevator with no windows. This person feels a steady force pushing them toward the floor. The question is, are they standing still on the surface of a planet where gravity is pulling them down, or are they inside a rocket accelerating upward through empty space, where the floor is pushing up on them? The answer, Einstein realized, is that there's no way to tell. Not by dropping objects, not by weighing things, not by any local experiment you can do inside that elevator. The experience of standing in a gravitational field feels identical to the experience of being accelerated. Locally, in a small enough region of space, acceleration and gravity are completely interchangeable. This is only possible because inertial and gravitational mass are the same. If they were different, you could distinguish the two situations. Objects with different ratios of gravitational to inertial mass would fall at different rates in a gravitational field, but accelerate identically when the elevator itself is accelerating. But since the ratios are always the same, the two scenarios produce indistinguishable results. The ledger adds a note in the margins here. Locally, acceleration and gravity cannot be distinguished, and it underlines the implication. The mass that resists acceleration and the mass that responds to gravity are not just numerically equal, They're the same thing, playing the same role in two different contexts. This brings up an important point about how the ledger is filled out in the first place. Who's writing these entries? Who's measuring these masses and accelerations? The answer is, any observer can, but different observers might write down different numbers for some quantities. This is the concept of reference frames. An observer standing on a train platform sees a train moving past at high speed. An observer sitting inside that train sees the platform moving. They're both right. Motion is relative. What counts as at rest and what counts as moving depends on your reference frame, on how you yourself are moving. In the ledger, this means that position and velocity entries depend on who's keeping the book. The same object might be at rest in one frame and moving in another. But mass? Mass is frame independent in classical physics. Every observer agrees on the mass of an object, even if they disagree about whether it's moving or how fast. Inertial mass is the stable number that everyone can write in the same column, the common ground between different perspectives on motion. Of course, in real life, observing inertia isn't always as clean as these idealized experiments suggest. Friction, air resistance, and other forces can muddy the picture. If you try to push a heavy box across a carpeted floor, it feels much harder than pushing the same box across a smooth ice rink. Does that mean the box's mass changed? Not at all. The box has the same inertial mass in both situations. The difference is that on carpet, friction is fighting your push, requiring extra force just to overcome the resistance of the surface. On ice, friction is minimal, so almost all of your force goes into accelerating the box. The ledger keeps a separate section for these parasitic forces. They're important in the real world, but they're not part of the object's intrinsic reluctance to accelerate. In a tidy thought experiment or a well-designed lab setup, we try to strip away friction and drag so we can see inertia clearly, unobscured by environmental complications. The true mass entry is independent of surfaces and air, and all the messy details of everyday life. There's another page in the ledger where mass shows up, this time in the context of energy. When you do work on an object, when you apply a force over a distance, you change its kinetic energy, the energy of its motion. The amount of kinetic energy an object has depends on its mass and its speed. Specifically, kinetic energy is 1/2 times mass times velocity squared. Mass determines how much energy is tied up in a given amount of motion. A fast-moving bowling ball carries a lot of kinetic energy because of its large mass. A fast-moving marble carries much less, even at the same speed, because its mass is small. And if you want to change an object's speed, you have to add or remove energy, with mass acting as the conversion factor between speed and energy. Later, in the early 20th century, Einstein showed that this connection between mass and energy goes even deeper. His famous equation, energy equals mass times the speed of light squared, suggests that mass itself is a form of energy. The ledger grows an extra cross-reference between the mass column and the energy pages, hinting that inertia, the resistance to acceleration, is fundamentally tied to how much energy content an object carries. But Einstein's insights didn't stop there. When he moved from special relativity to general relativity, he reimagined the entire picture of gravity and inertia. Instead of thinking of gravity as a force that pulls on masses from a distance, he described it as the curvature of space-time itself. Mass and energy shape the geometry of the space and time around them, and objects simply follow the straightest possible paths, called geodesics, through that curved geometry. In this picture, inertia is still the tendency to move along natural paths. An object left alone follows a geodesic in space-time, which might look like a straight line in flat space or a curved orbit near a massive body. The ledger updates its definitions, replacing force language with geometry language, but the core idea remains. Objects resist changes to their natural motion unless something intervenes, either an actual force pushing them off their geodesic or a change in the curvature of space-time itself. And the equivalence of inertial and gravitational mass? In general relativity, that becomes a foundational principle, not just an observed coincidence. It's called the equivalence principle, and it states that inertial mass and gravitational mass are not merely equal. They are the same property viewed from different angles. This principle is what allows Einstein to describe gravity as geometry rather than force. If the mass that resists acceleration were different from the mass that responds to gravity, the whole framework would collapse. The ledger underlines one key sentence here. The mass that resists acceleration is the same mass that responds to gravity. It's a unifying entry that ties together all the seemingly separate threads, falling objects, accelerating carts, orbits, reference frames, into one coherent story. Physicists have tested this equality with ever-increasing precision over the decades. Galileo supposedly dropped weights from the Leaning Tower of Pisa, though the story may be apocryphal. Newton used pendulums. In the 19th century, the Hungarian physicist Ert Vues designed torsion balances that could detect tiny differences in how objects fall. In the 20th and 21st centuries, experiments have used laser interferometers, satellite measurements, atom interferometers, and other sophisticated techniques. Each new experiment refines the error bars, tightening the limits on any possible discrepancy between inertial and gravitational mass. So far, every test has come up empty. The two quantities match to 1 part in a trillion or better, depending on the experiment. In the ledger, the discrepancy column is filled with zeros, and the uncertainty gets smaller and smaller with each passing decade. It's a quiet testament to the robustness of this strange equality, a cosmic coincidence that isn't a coincidence at all, but something much deeper. There are a few special cases worth noting, entries in the ledger that don't quite follow the usual pattern. Some entities, like photons, particles of light, have no rest mass at all. Their mass entry is 0. They don't resist acceleration in the traditional sense because they always travel at the speed of light in vacuum. They can't be sped up or slowed down. They carry energy and momentum, and they respond to gravity by bending their paths near massive objects, but they fit into a different category in the ledger. Mass equals 0, governed by different rules. The presence of massless particles helps clarify what it means for an object to have inertial mass. Mass is what gives an object the ability to have different speeds, to be at rest or moving, to accelerate gradually under a force. Photons, lacking mass, skip all that. They're always moving at light speed, always following null geodesics in space-time. They're a limiting case that highlights the role mass plays for everything else. But most of the ledger is filled with ordinary objects, the kinds of things you encounter every day. And inertial mass shows up constantly in everyday experience, even if we don't always think of it in those terms. Consider a heavy door. When you push it open, it resists at first, requiring a noticeable force to get it moving. That's inertia. The door's mass resists the change from rest to motion. Once it's moving, it wants to keep moving. So if you stop pushing, it might swing a bit farther before friction and air resistance bring it to a stop. A light door, by contrast, starts moving easily and stops easily. Less mass means less inertia, less resistance to changes in motion. Or think about driving a car. When you press the accelerator, the engine applies a force, and the car speeds up, but not instantly. The car has significant mass, and that mass resists acceleration. The heavier the car, the more sluggish the acceleration feels. When you take your foot off the accelerator, the car doesn't stop immediately either. It coasts forward, its inertia keeping it moving until friction and air resistance gradually slow it down. When you brake, you're applying a force to decelerate the car, fighting against its inertia. Or picture holding a cup of coffee in your hand as you walk. If you start walking suddenly, the coffee sloshes backward. If you stop suddenly, it sloshes forward. The liquid has mass, and it resists changes in velocity. When you accelerate, the cup accelerates because you're holding it, but the coffee inside wants to keep moving at its previous velocity. It lags behind, sloshing backward relative to the cup. When you decelerate, the coffee wants to keep moving forward, so it sloshes forward relative to the cup. Every slosh is a little demonstration of inertia at work. These are small, mundane examples, but they're everywhere. The ledger doesn't only apply to laboratory equipment or astronomical bodies, it applies to everything. Every door, every vehicle, every drop of liquid has its entry. The reluctance to speed up, slow down, or change direction is just that object's mass quietly appearing in the attendance list, asserting itself in the world. Think about a child on a playground swing. When the swing is at rest, it takes effort to get it moving. You have to push, applying force to overcome the combined inertia of the swing and the child. Once it's swinging, though, it wants to keep swinging. The child pumps their legs, adding energy at just the right moments to maintain or increase the amplitude. If they stop pumping, friction at the pivot and air resistance gradually steal that energy away, and the swing's motion decays. But the initial reluctance to start the tendency to continue once moving, the need for continuous input to fight dissipative forces, all of these trace back to the mass entry in the ledger. Or consider throwing a ball. The moment your hand releases the ball, it continues moving in the direction you threw it. Its inertia carries it forward. Gravity pulls it downward, curving its path into an arc, but horizontally the ball maintains its initial velocity quite well, at least until air resistance becomes significant. A heavier ball, thrown with the same force, won't travel as far because its greater mass means it accelerates less during the throw, leaving your hand with less speed. A lighter ball accelerates more easily, achieving higher speed for the same throwing force, though it's also more affected by air resistance once in flight. The interplay between mass, force, and acceleration determines every aspect of the ball's trajectory. Inside machines, inertia becomes something engineers must account for very carefully. A flywheel in an engine is designed with significant mass specifically to resist changes in rotational speed. It smooths out variations in power delivery, using its inertia to keep rotating steadily, even when the force from combustion is pulsing on and off. The ledger entry for a flywheel is large on purpose, a deliberate choice to harness inertia as a stabilizing force. Conversely, in precision instruments like robotic arms or telescope mounts, engineers try to minimize inertia where possible. They want the device to respond quickly to control inputs, to start and stop with minimal lag. They use lightweight materials and clever designs to reduce the mass that needs to be accelerated. The ledger entry for each moving part is kept as small as practical, making the system agile and responsive. In space, inertia takes on an especially pure form because there's no air resistance, no friction from surfaces, nothing to obscure the fundamental behavior. A spacecraft coasting through the vacuum continues in a straight line, at constant velocity indefinitely, barring gravitational influences or deliberate thruster firings. When astronauts push off from a wall inside the International Space Station, they glide smoothly to the opposite wall, their inertia carrying them forward until something stops them. The ledger's basic rule, objects maintain their motion unless acted upon, becomes strikingly visible in this environment. Maneuvering in space also reveals how inertia governs rotation, not just straight-line motion. An object's resistance to rotational acceleration is called rotational inertia, or moment of inertia, and it depends not just on mass, but on how that mass is distributed relative to the axis of rotation. A figure skater pulling their arms in during a spin decreases their moment of inertia, and conservation of angular momentum causes them to spin faster. Push their arms back out, and the moment of inertia increases, slowing the spin. The ledger has an entire subsection for rotational entries, a parallel counting system for spins and tumbles. Back on Earth, we see rotational inertia when we try to open a door by pushing near the hinges versus pushing near the handle. Pushing near the handle is much easier because the door's mass is farther from the axis of rotation, making it more responsive to torque applied at that point. The door's rotational inertia hasn't changed, but the mechanical advantage of applying force farther from the pivot means you get more angular acceleration for the same effort. The ledger notes this geometry-dependent behavior, reminding us that inertia isn't just about mass in isolation, but about how that mass relates to the motion in question. Athletes intuitively understand inertia, even if they never think about it in those terms. A baseball pitcher throwing a fastball generates force through their entire body, transferring momentum from legs to hips to torso to arm to hand to ball. Each segment has its own mass and inertia, and the pitcher's technique is all about sequencing these accelerations to maximize the ball's final velocity. A gymnast executing flips and twists manipulates their body's moment of inertia, tucking tight to spin faster, extending to slow down, controlling their rotation through precise changes in mass distribution. In architecture, structural engineers must account for the inertia of buildings during earthquakes. A massive skyscraper has enormous inertia. When the ground shakes, the building's base moves with the earth, but the upper floors want to remain where they are due to inertia. This creates shear forces within the structure. Engineers design buildings with flexibility and damping systems to absorb and dissipate this energy, preventing the inertia of the building's mass from tearing the structure apart. The ledger entry for a skyscraper is huge, and that mass becomes a critical factor in seismic design. Similarly, bridges must handle dynamic loads, traffic, wind, even resonant oscillations. When a heavy truck crosses a bridge, the bridge deck deflects slightly under the weight. But the truck also has inertia. If the bridge deck is bouncing from the passage of previous vehicles, the truck's inertia resists being accelerated up and down with those oscillations. The interaction between the bridge's flexibility and the truck's inertia can create complex dynamic behaviour. Engineers model these interactions carefully, consulting the ledger entries for vehicles, bridge components, and even wind-driven masses of air to ensure stability. Water has inertia too, of course, and it becomes important in hydraulic systems and fluid dynamics. When you suddenly close a valve in a pipe carrying fast-moving water, the water's inertia doesn't let it stop instantly. The moving column of water slams into the closed valve, creating a pressure surge called water hammer that can damage pipes or even burst them. The ledger entry for the water, its mass times its velocity, determines how violent this surge will be. Plumbing engineers design systems with air chambers or slow-closing valves to manage the inertia of flowing fluids. In the oceans, the inertia of water masses drives large-scale circulation patterns. Currents, once established, persist because the vast volume of moving water has enormous inertia. Even when the wind that started a current dies down, the current continues for a long time, slowly dissipating its kinetic energy through friction and turbulence. The Gulf Stream, the Kuroshio Current, the Antarctic Circumpolar Current, all are entries in the ledger with truly staggering mass values, and their inertia makes them stable features of Earth's climate system over years and decades. The atmosphere too has inertia. Air masses moving across continents maintain their trajectories, bending gradually due to the Coriolis effect and pressure gradients, but resisting sudden changes. A hurricane is a dramatic example, a rotating mass of air with such enormous angular momentum that it takes days to spin down, even after it makes landfall and loses its energy source. The ledger entry for a hurricane's rotating mass explains why these storms are so persistent and destructive. Even on the smallest scales, inertia appears. Individual atoms and molecules have mass, and they resist acceleration just like macroscopic objects do. In a gas, molecules are constantly bouncing around, colliding with each other and the container walls. Each collision is governed by the same inertial principles. Momentum is conserved, with the molecules' masses determining how their velocities change in each impact. The pressure a gas exerts on a container is the cumulative result of countless tiny inertial interactions, molecular masses in motion, transferring momentum to the walls. In particle accelerators, physicists manipulate the inertia of subatomic particles with exquisite precision. Charged particles like protons are accelerated to nearly the speed of light using electromagnetic fields. As the particles gain energy and speed, their relativistic mass increases, making them harder to accelerate further. The ledger has to be updated for relativistic effects here. At very high speeds, mass is no longer constant but grows with velocity, asymptotically approaching infinity as the particle nears light speed. This is why accelerating a particle to exactly the speed of light would require infinite energy. Its inertial resistance grows without bound. Yet for all its ubiquity and usefulness, inertial mass still holds mysteries. Physics uses it extraordinarily well. We can measure it, predict with it, build technologies around it. But some deeper questions remain open, written in a Y column in the ledger with notes marked under investigation. Why do particles have the masses they have? Why does an electron have the mass it does, and a proton a different mass, and a neutron yet another? These aren't arbitrary numbers, but we don't fully understand what determines them. The Higgs field, discovered in experiments at the Large Hadron Collider, provides a mechanism. Particles acquire mass by interacting with this field. But that just pushes the question back a step. Why does the Higgs field exist? Why does it have the properties it has? Why do different particles couple to it with different strengths? The standard model of particle physics includes these mass values as input parameters, numbers that must be measured experimentally rather than derived from the theory itself. The ledger records them accurately, but it can't explain where they come from. There's a sense that a deeper theory should predict these masses, should tell us why the electron weighs what it does and not something else. But we're not there yet. The Y column has a note. Mechanism identified, deeper origin unknown. And why do inertial and gravitational mass match so perfectly? General relativity builds this equality in as a foundational principle, but it doesn't explain it in terms of something more fundamental. It's a postulate, an assumption that works beautifully and has been confirmed by countless experiments, but it's not derived from anything deeper within the theory. Some physicists hope that a more complete theory of quantum gravity might eventually explain why this equivalence holds, rooting it in the underlying structure of space-time and matter at the smallest scales. String theory, loop quantum gravity, and other candidate theories of quantum gravity all grapple with this question in different ways. They suggest that at the Planck scale, distances around 10 to the negative 35 meters, where quantum effects and gravitational effects become equally important, space and time themselves might have a discrete granular structure. In such a picture, inertia and gravity might emerge from the same fundamental quantum properties of space-time geometry. But these theories are not yet complete or confirmed by experiment. The ledger notes them in the margins as speculative frameworks under development. There's also the puzzle of dark matter. Astronomical observations strongly suggest that most of the mass in the universe is invisible, interacting only through gravity and not through electromagnetic forces. This dark matter has inertial mass. It resists acceleration, clusters under its own gravity, forms the scaffolding for galaxies to assemble. But we don't know what it's made of. The ledger has entries for dark matter halos around galaxies, enormous masses inferred from their gravitational effects, but the entries are annotated with composition unknown. Whatever dark matter is, it has both inertial and gravitational mass, and those masses are equal just like they are for ordinary matter, but beyond that we're still searching for answers. Then there's the mystery of mass's relationship to the vacuum itself. Quantum field theory describes empty space not as truly empty, but as seething with virtual particles, fleeting fluctuations in fields that pop in and out of existence. These fluctuations contribute to the properties of particles moving through the vacuum. In a sense, a particle's inertia might arise partly from its interaction with these vacuum fluctuations, from the way the vacuum pushes back when the particle is accelerated. This idea, sometimes called vacuum inertia, is still being explored and debated. The ledger adds another marginal note. Possible connection between inertia and vacuum structure requires further theoretical development. Even the concept of mass becomes slippery when you probe deeply enough. In quantum mechanics, particles are also waves, described by probability distributions rather than definite positions and velocities. The mass of a particle appears in the Schrödinger equation, determining how the wave function evolves over time. A more massive particle has a wave function that changes more slowly in response to potential energy changes. Another manifestation of inertia, quantum inertia if you will, resistance to changes in the wave's shape and motion. The ledger notes this quantum interpretation, acknowledging that mass plays its stubborn role even in the probabilistic realm of wave functions. And what about antimatter? Every particle has an antimatter counterpart with the same mass but opposite charge. An electron and a positron, for example, have identical inertial and gravitational masses as far as we can measure, but some theories speculate that antimatter might have slightly different gravitational behavior, perhaps even experiencing gravitational repulsion rather than attraction. This is deeply controversial and not supported by experiments so far, but it's being tested. Experiments at CERN are measuring how antihydrogen atoms fall in Earth's gravitational field, checking whether antimatter's gravitational mass really does equal its inertial mass just like ordinary matter. The ledger has a footnote here, assumed equal for antimatter, experimental verification in progress. These open questions don't undermine the usefulness of inertial mass in everyday physics and engineering. The ledger works perfectly well for designing cars, predicting planetary orbits, analysing collisions, building accelerators. The entries are accurate, the calculations reliable. But the deeper mysteries remind us that even the most familiar, most thoroughly tested concepts in physics rest on foundations we don't fully understand. The why column is still being filled in slowly through research and experimentation and theoretical exploration. It's another tab in a very patient file, a reminder that science is never truly finished, that every answer opens new questions, and so we close the attendance ledger for the night. Inertial mass, in this telling, is nothing more and nothing less than the universe's way of recording how hard each object is to budge. Every cart, every planet, every particle in existence has its name written in the book, with a single number beside it that controls both how quickly it accelerates when pushed and how strongly it falls in a gravitational field. It's a quiet number, unassuming, written in steady handwriting across countless pages, but it governs everything that moves or stays still, everything that resists or yields, everything that falls or orbits or collides. The ledger sits on a shelf somewhere in the filing cabinet of physics, one of the most fundamental reference books the universe keeps. Each entry reads simply, reluctant to change motion unless something really insists. As you drift off tonight, you can picture that shelf, that ledger, those neat columns of names and numbers, the marble and the bowling ball, the empty cart and the loaded one, the feather and the hammer falling together in airless silence, the door that resists your push, the car that coasts when you stop accelerating, the coffee that sloshes in your cup, the flywheel smoothing an engine's pulses, the spacecraft gliding through vacuum, the hurricane refusing to dissipate. All of them present and accounted for, each with its own measure of stubbornness, its own resistance to being pushed around. And in the morning, when you open a heavy door or feel a car accelerate beneath you, or watch waves roll persistently toward shore, you'll recognize it, that same quiet number, showing up again, doing exactly what the ledger says it should do, resisting, persisting, insisting on its right to keep doing whatever it was already doing until something convinces it otherwise. The attendance has been taken, the masses have been recorded, and the universe continues its patient accounting, one stubborn object at a time. The next story is about to begin. Please relax and enjoy. The first thing to understand about Earth's tectonic plates is that they are not dramatic. They do not rush. They do not announce themselves with fanfare. They simply exist, drifting across the planet's surface at roughly the speed your fingernails grow, clocking in and out of their shifts with all the excitement of a filing cabinet being moved 1 millimeter to the left every decade. If you were to sit and watch a continent move, you would die of boredom long before you died of old age. You would see nothing. You would feel nothing. And yet, over spans of time so vast they make human history look like a sneeze, these plates accomplish everything. They build mountains, carve ocean basins, recycle the seafloor, and shuffle continents around the globe like a very slow card dealer with infinite patience. Think of the Earth's lithosphere, the rigid outer shell that includes the crust and uppermost mantle, as a vast office complex. It is divided into roughly a dozen major plates and several dozen smaller ones, each one a slab of rock anywhere from 70 to 200 kilometers thick, floating atop a softer, slowly churning layer called the asthenosphere. The asthenosphere is not liquid, but it behaves like one over geologic time, a kind of very slow conveyor belt made of hot, ductile rock that moves at rates measurable only with precision instruments. The plates themselves are the employees of this office, and they have shifts, they have routes, they have tasks. Some are growing, some are shrinking, some are colliding in the break room. None of them are in a hurry. Let us begin with the mid-ocean ridges, which are the onboarding desks of the tectonic world. These are underwater mountain ranges that snake through the ocean basins, places where two plates are pulling apart and new crust is being created. The process is called seafloor spreading, and it happens at a pace so slow that if you were standing on the ridge itself, deep underwater, in the dark, under crushing pressure, you would not notice anything happening at all. But over millions of years, magma wells up from the mantle, cools, solidifies, and becomes new oceanic crust. This new crust is added to the edges of the diverging plates, pushing them slowly apart. It is a conveyor belt running in reverse, manufacturing rock as it goes. The Mid-Atlantic Ridge is one of the most well-known examples. It runs down the center of the Atlantic Ocean, roughly tracing the seam between the Eurasian and North American plates on one side and the African and South American plates on the other. Every year, the Atlantic Ocean widens by about 2.5 centimeters. That is roughly the rate at which your hair grows. If you were born on the coast of Portugal and lived your entire life there, the coast of North America would move away from you by about 2 meters, less than the length of a small car. Over the course of 200 million years, however, this same process has opened an entire ocean basin. The Atlantic did not exist when dinosaurs first appeared. It was created centimeter by centimeter, shift by shift, with no days off. At the mid-ocean ridge, the new crust is hot, fresh, and buoyant. It sits high on the seafloor, forming the ridge itself. As it moves away from the ridge, it cools, contracts, and sinks, creating the deep abyssal plains that make up most of the ocean floor. This is not a violent process. There are no explosions. Occasionally, There is volcanic activity, slow, oozing eruptions of basaltic lava that form pillow-shaped blobs on the seafloor. But even these are quiet, hidden under kilometers of water, witnessed only by strange eyeless fish and the occasional research submarine. The ridge is a place of creation, but it is a place of profound tedium. If there were a break room here, it would have stale coffee and a microwave that takes too long. Now consider the opposite end of the shift, the subduction zones. These are the retirement chutes, the places where old oceanic crust, having spent millions of years slowly cooling and sinking, finally reaches the edge of its life and is pulled back down into the mantle. Subduction occurs where an oceanic plate collides with another plate, either another oceanic plate or a continental plate, and the denser of the two is forced downward. The oceanic plate, being colder and heavier, slides beneath the other and descends into the mantle at an angle, a process that can continue for hundreds of kilometers into the Earth's interior. The Mariana Trench, the deepest place on Earth, is a subduction zone. Here, the Pacific Plate is being shoved beneath the smaller Mariana Plate at a rate of a few centimeters per year. The trench itself is nearly 11 kilometers deep, a gash in the ocean floor so profound that if you placed Mount Everest inside it, the peak would still be covered by more than 2 kilometers of water. But the trench is not a wound. It is simply the surface expression of a plate going off duty, descending slowly into the mantle where it will be heated, melted, and eventually recycled into new magma. This is Earth's way of taking out the trash. It is efficient. It is boring. It takes millions of years. Subduction is not entirely peaceful. As the descending plate grinds past the overriding plate, friction builds up. Stress accumulates. Eventually the plates slip, and the stored energy is released as an earthquake. These quakes can be devastating, but from the perspective of the plates themselves, they are just minor adjustments, tiny hiccups in an otherwise smooth descent. The 2011 Tohoku earthquake in Japan, which triggered a massive tsunami, and the Fukushima nuclear disaster, was caused by the Pacific Plate lurching a few meters downward beneath the North American Plate. To a human, this was catastrophic. To the plates, it was a momentary stumble on a journey that has been underway for 50 million years and will continue for 50 million more. Above, subduction zones, volcanic arcs often form. These are chains of volcanoes that grow on the overriding plate, fed by magma generated as the descending plate releases water into the mantle, lowering the melting point of the surrounding rock. The Andes, the Cascades, the Japanese archipelago, all are products of subduction. But again, these are slow-motion features. A volcano might erupt spectacularly every few decades or centuries, but the mountain itself grows over millions of years, built layer by layer from eruptions that are, geologically speaking, routine maintenance. Then there are the transform faults, the sideways shuffles, the hallway encounters where two plates slide past each other horizontally without creating or destroying crust. These are the places where plates are simply trying to get past one another, like two co-workers squeezing by in a narrow corridor, each moving in the opposite direction. The San Andreas Fault in California is the most famous example. Here, the Pacific Plate is sliding northward relative to the North American Plate at about 5 centimeters per year. Over the past 20 million years, this motion has carried fragments of California hundreds of kilometers northward. Eventually, in another few tens of millions of years, Los Angeles will be adjacent to San Francisco. The two cities are not rushing toward one another. They're being carried along on their respective plates, inching closer, taking their time. Transform faults do not look like much on the surface. The San Andreas is visible in places as a linear valley or a series of offset stream channels, but much of it is unremarkable. There are no mountains being built here, no trenches being dug, just lateral motion. And yet, because the plates do not slide smoothly, they catch, stick, and then jerk forward. The fault is capable of producing large earthquakes. The 1906 San Francisco earthquake was caused by a sudden slip of up to 6 meters along the northern section of the fault. But that slip was the culmination of decades or centuries of slow, silent strain accumulation. The earthquake was the exception. The rule is stillness. Continental collisions are the longest meetings in Earth's office, the kind where everyone knows the outcome but the paperwork takes forever. When two continental plates collide, neither can subduct because both are too buoyant. Continental crust is thick, old, and light compared to oceanic crust. It floats high on the mantle, so when two continents meet, they crumple, fold, and thicken. building mountains in a process that unfolds over tens of millions of years. The Himalayas are the result of the Indian plate colliding with the Eurasian plate, a collision that began around 50 million years ago and continues today. India is still pushing northward at about 5 centimeters per year. The Himalayas are still rising, though erosion is simultaneously wearing them down. The mountains are not a finished product. They are a work in progress, a very slow work in progress, like a novel being written one word per decade. The collision that formed the Himalayas also closed an ancient ocean called the Tethys, which once separated India from Asia. The floor of that ocean was subducted, pulled down into the mantle and erased. Only a few fragments remain, preserved as slivers of oceanic crust now stranded high in the mountains, a reminder that the highest peaks on Earth were once underwater. This is the nature of plate tectonics. Nothing is permanent. Oceans open and close, continents split and merge, mountains rise and erode. But all of it happens so slowly that, from a human perspective, the world seems static. Hotspots add another layer to the schedule. These are places where plumes of unusually hot mantle material rise from deep within the Earth, punching through the overlying plate and creating volcanic activity. Unlike the volcanoes at plate boundaries, hotspots are stationary, or at least they move much more slowly than the plates themselves. As a plate drifts over a hotspot, a chain of volcanoes is created, each one forming directly above the plume and then being carried away as the plate moves on. The Hawaiian Islands are a classic example. The big island of Hawaii currently sits over the Hawaiian hotspot and is volcanically active. To the northwest, older islands in the chain are extinct, having been carried away from the hotspot by the motion of the Pacific plate. The oldest islands are eroded, subsided, and barely visible above sea level. Farther northwest still, the chain continues as a series of underwater seamounts, ancient volcanoes that have long since sunk below the waves. The entire chain stretches for thousands of kilometers, a record of the Pacific plate's motion over the past 70 million years, written in volcanic rock. Hotspots are rare. There are only a few dozen known examples worldwide. Most of them are in oceanic settings, but a few occur beneath continents. The Yellowstone hotspot, currently beneath Wyoming, has left a trail of volcanic calderas across the western United States as the North American plate has drifted southwestward over it. The hotspot itself is thought to be fed by a mantle plume rising from near the core mantle boundary, nearly 3,000 kilometers below the surface. It is a slow, steady upwelling of heat, and it has been active for at least 17 million years. Every few 100,000 years it produces a super eruption, emptying a magma chamber and collapsing the surface into a caldera. The last such eruption occurred about 640,000 years ago. Another will happen eventually, but probably not for another few 100,000 years. Geologic time is patient. Supercontinent cycles are the longest items on the plate ledger, the kind of project that spans hundreds of millions of years and involves every plate on Earth. Continents drift, collide, and assemble into a single massive landmass, which then breaks apart and disperses, only to eventually reassemble again in a different configuration. The most recent supercontinent was Pangaea, which existed around 300 million years ago. It began to break apart about 200 million years ago, splitting into Laurasia in the north and Gondwana in the south, which then fragmented further into the continents we know today. Before Pangaea, there was Rodinia, which formed about 1 billion years ago and broke apart around 750 million years ago. Before Rodinia, there was likely another supercontinent and another before that, stretching back billions of years into Earth's history. The assembly and breakup of supercontinents is driven by the same processes that move plates today: seafloor spreading at mid-ocean ridges, subduction at ocean trenches, and continental collision. But these processes play out on such vast timescales that the entire cycle, from dispersed continents to supercontinent and back again, takes about 500 million years. We are currently in the dispersal phase. The Atlantic is opening, the Pacific is shrinking. In a few 100 million years, the continents may collide again, forming a new supercontinent. Some geologists call this hypothetical future landmass Pangaea Ultima. Others have proposed different configurations with names like Amasia or Novo Pangaea. No one knows exactly what will happen, but the cycle will continue. It always does. Seismic belts are where the action is, geologically speaking, though even here action is a relative term. Most of the world's earthquakes and volcanic eruptions occur along plate boundaries, particularly at subduction zones and transform faults. These regions form linear belts that wrap around the planet. The Ring of Fire, which encircles the Pacific Ocean, is the most active seismic belt on Earth, home to about 75% of the world's active volcanoes and 90% of the world's earthquakes. But even in the Ring of Fire, most of the time nothing is happening. The plates are locked, silently accumulating strain. The volcanoes are dormant, their magma chambers slowly refilling. And then, occasionally, there is a release, an earthquake, an eruption, a reminder that the plates are still on the clock. Intraplate earthquakes, which occur far from plate boundaries, are rarer and less well understood. The New Madrid earthquakes of 1811 and 1812, which struck the central United States, were intraplate events. They were powerful, possibly magnitude 7 or greater, and they rang church bells as far away as Boston. But they occurred in the middle of the North American plate, far from any active boundary. Geologists believe they were caused by ancient faults and weaknesses in the crust, remnants of past tectonic events that are still capable of slipping under the right conditions. These earthquakes are reminders that even the stable interiors of plates are not entirely inactive. They are just very, very slow. Plate velocities vary. Some plates, like the Pacific Plate, move relatively quickly, up to 10 centimeters per year. Others, like the Eurasian Plate, move more slowly, just a centimeter or two per year. These differences are driven by the balance of forces acting on each plate, the push from mid-ocean ridges, the pull from subducting slabs, the resistance from friction at plate boundaries. Larger plates with more subducting edges tend to move faster because the sinking slabs pull the rest of the plate along, a process called slab pull. Smaller plates, or those without much subduction, move more slowly. But even the fastest plates are slow. 10 centimeters per year is about the rate at which bamboo grows. It is not nothing, but it is not fast. The asthenosphere beneath the plates is also in motion, driven by convection currents that transport heat from the Earth's interior to the surface. Hot material rises, cools, and sinks in a slow churning cycle that operates on timescales of millions of years. The details of mantle convection are still debated. Some models suggest large-scale circulation cells that span the entire mantle. Others propose multiple layers of convection, with the upper and lower mantle largely decoupled. What is clear is that the mantle is not static. It flows, and that flow drives the motion of the plates above. The plates are not passive passengers. They are part of the system, dragging mantle material along with them as they move, influencing the flow below. The Wilson cycle, named after the Canadian geophysicist J. Tuzo Wilson, describes the life cycle of an ocean basin from birth to death. It begins with rifting, where a continent splits apart and a new ocean basin opens. The Red Sea and the East African Rift are examples of this stage. The basin then widens as seafloor spreading continues, creating a mature ocean like the Atlantic. Eventually, subduction begins along the ocean's margins, and the basin starts to close. The ocean shrinks, and the continents on either side move closer together. Finally, the continents collide, the ocean is completely consumed, and a mountain range is built. The cycle then begins again as the newly formed supercontinent eventually rifts apart. The Wilson cycle is not a rapid process. Each complete cycle takes hundreds of millions of years. We are witnessing only a single frame of a very long film. Ophiolites are fragments of ancient oceanic crust that have been thrust up onto continents during collisions, preserved as a kind of geologic fossil. They provide a rare opportunity to study oceanic crust up close, without having to drill through kilometers of ocean or descend into deep trenches. Ophiolites typically consist of a layered sequence: pillow basalts at the top, sheeted dikes below, then gabbro, and finally peridotite from the upper mantle. This sequence represents a cross-section through the oceanic lithosphere, frozen in place and exposed at the surface. Ophiolites are found in mountain belts around the world, from the Alps to Oman to Newfoundland, each one a remnant of an ocean that no longer exists. Paleomagnetism has been crucial in reconstructing the history of plate motions. When volcanic rocks cool, magnetic minerals within them align with the Earth's magnetic field, recording the direction and intensity of that field at the time. By studying these magnetic signatures in rocks of different ages, Geologists can determine where a plate was located in the past and how it has moved over time. Paleomagnetic data revealed that the continents have not always been in their current positions, providing some of the earliest evidence for continental drift. The data also showed that the Earth's magnetic field reverses polarity at irregular intervals, with north and south magnetic poles switching places. These reversals are recorded in the oceanic crust as alternating stripes of normal and reversed magnetism, symmetrically arranged on either side of mid-ocean ridges. The pattern was one of the key pieces of evidence that confirmed the theory of seafloor spreading in the 1960s. The theory of plate tectonics itself is relatively young. Alfred Wegener proposed the idea of continental drift in the early 20th century, based on the fit of the continents, the distribution of fossils, and the matching of mountain ranges across oceans. But his ideas were largely dismissed because he could not explain the mechanism by which continents moved. It was not until the 1950s and 60s, with the advent of oceanographic research and the discovery of seafloor spreading, that the pieces came together. The theory of plate tectonics was formalized in the late 1960s and quickly became the unifying framework for understanding Earth's geology. It explained earthquakes, volcanoes, mountain building, and the distribution of rocks and fossils. It connected processes happening at the surface with processes deep in the mantle, and it did so with a mechanism that was slow, steady, and entirely consistent with the geologic record. Plate tectonics is not unique to Earth. Venus, similar in size and composition to Earth, does not appear to have plate tectonics. Its surface is dominated by volcanic plains and highlands, with no clear evidence of subduction or seafloor spreading. Mars once had a magnetic field, which suggests it may have had some form of plate motion early in its history, but that activity ceased billions of years ago. The icy moons of Jupiter and Saturn show signs of tectonics, but driven by ice rather than rock. Europa, for example, has a surface covered in cracks and ridges, evidence of a thin icy shell floating on a subsurface ocean. But true plate tectonics, with the continuous creation and destruction of lithosphere, seems to be rare. It requires a planet with the right size, temperature, and composition. Earth happens to be in that sweet spot. The plates will continue there, work long after humans are gone. The Atlantic will keep widening, the Pacific will keep shrinking, Africa will split along the East African Rift, creating a new ocean basin. Australia will continue drifting northward, eventually colliding with Asia. The Himalayas will keep rising until erosion and the eventual halt of the collision bring them down again. In a few 100 million years, the continents will assemble into a new supercontinent, reshape the climate, and alter the distribution of life. And then, eventually, that supercontinent will break apart and the cycle will begin again. None of this will happen quickly. None of it will be visible in a human lifetime. But it will happen, just as it has happened countless times before. There is something deeply calming about the slowness of it all. In a world that often feels frantic and unpredictable, the tectonic plates are a reminder that some processes are beyond our control and beyond our timescale. They do not care about human events. They do not notice our cities, our borders, or our conflicts. They simply drift, collide, and subduct, following the same basic rules they have followed for billions of years. They clock in, perform their tasks, and clock out shift after shift, in a routine so slow and so vast that it becomes almost meditative. The plates are not conscious, of course. They do not have intentions or goals. They are driven by heat and gravity, by the cooling of the Earth's interior and the convection of the mantle. But if we were to anthropomorphize them, we might imagine them as the most patient workers in the universe, content to do their jobs without recognition, without complaint, and without any expectation of ever finishing. The work is never done. There is always more crust to create, more seafloor to recycle, more mountains to build. And so they continue, centimetre by centimetre, year by year, eon by eon. Human infrastructure, by comparison, is ephemeral. A building lasts decades. A road lasts a century if it is well maintained. A dam might last a few centuries. But even the most durable human-made structures are temporary on geologic timescales. The plates will outlast them all. The San Andreas Fault will eventually tear through every structure ever built in California. The Himalayas will rise and erode, burying and then exhuming whatever traces of human civilization happen to be in their path. The Atlantic will widen until it begins to close again, and when it does, the entire eastern seaboard of North America will be crumpled into a new mountain range. None of this is a threat. It is simply the way the Earth works. Geologists who study plate tectonics spend their careers reconstructing the past positions of continents, mapping ancient plate boundaries, and modelling the forces that drive plate motion. They work with data from seismology, geochronology, paleomagnetism, and satellite geodesy. They drill cores from the seafloor and measure the ages of rocks on every continent. They build computer simulations that track the motion of plates over millions of years, rewinding and fast-forwarding through Earth's history like a very slow film. And through all of this work, a picture emerges. The plates have been moving for at least 3 billion years, and they will continue moving for billions more until the Earth's interior cools enough that convection ceases and the mantle solidifies. That day is billions of years away. There is no drama in plate tectonics, not really. There are earthquakes, yes, and volcanic eruptions and tsunamis. These events are dramatic from a human perspective, and they can be devastating. But from the perspective of the plates, they are just small adjustments, minor glitches in an otherwise smooth operation. The real story of plate tectonics is not the earthquakes or the eruptions. It is the slow, relentless motion of the plates themselves. The opening and closing of ocean basins, the rise and fall of mountain ranges, the endless recycling of the Earth's crust. It is a story told not in days or years, but in millions and billions of years. It is a story without an ending, because the process is still underway. If you wanted to watch plate tectonics happen in real time, you would need patience beyond comprehension. You would need to sit in one place, unmoving, for millions of years. You would watch continents inch across the globe like shadows moving across a sundial. You would see mountains grow so slowly that their rise would be imperceptible, even over the span of multiple human lifetimes. You would watch the ocean floor spread, but only if you had instruments sensitive enough to measure centimeters over decades. And even then, you would spend most of your time watching nothing happen, because most of the time, nothing is happening. The plates are locked, the strain is building, the magma is cooling, everything is waiting. And then, occasionally there would be a lurch, a slip, a sudden release of energy, an earthquake lasting seconds or minutes, representing the culmination of decades or centuries of silent tension. Or a volcanic eruption, dramatic and violent, but ultimately just a small event in the life of a plate boundary that has been active for tens of millions of years. And then the waiting would resume. The plates would settle back into their slow drift. The strain would begin to build again, and the cycle would continue. This is the office of Earth's tectonic plates. It is not exciting. It is not fast. But it is thorough, and it is relentless, and over the timescales on which it operates, it accomplishes everything. It has shaped the surface of the planet. It has created the continents and the ocean basins. It has built the mountains and the valleys. It has influenced the climate, the evolution of life, and the distribution of resources. And it has done all of this without hurry, without fanfare, and without any concern for the fleeting dramas of the species that happen to be living on its surface at any given moment. The plates will keep drifting, the ridges will keep spreading, the trenches will keep subducting, the faults will keep slipping, and the world will keep changing 1 centimeter at a time in the most boring shift schedule the universe has ever devised. The thing about working on geologic time is that there are no sick days, no vacations, no union-mandated breaks. The plates do not stop for holidays, they do not pause for weekends. Christmas Day passes, and the Pacific Plate moves another fraction of a millimeter northward. New Year's Eve arrives, and the mid-Atlantic ridge extrudes another thin layer of basalt onto the seafloor, unwitnessed and uncelebrated. Every second of every day for the past several billion years, the plates have been in motion. The cumulative effect is staggering, but the moment-to-moment reality is pure tedium. Consider the paperwork involved. If Earth's plates were actual employees, their timesheets would be incomprehensible. A single shift might last 10 million years. The job description would read something like, slowly drift northward at 4 centimeters per year, occasionally subduct beneath adjacent plate, build volcanic arc as needed, submit seismic activity reports irregularly. Performance reviews would happen every 100 million years or so, and the feedback would always be the same. Continues to perform adequately. No significant changes noted. Recommend continuation of current trajectory. The managerial structure of plate tectonics is equally opaque. If anyone is in charge, it is the laws of thermodynamics. Heat flows from hot to cold. The Earth's interior, still warm from its formation 4.5 billion years ago and continuously heated by radioactive decay, loses heat to space. This heat must escape, and convection in the mantle is one of the primary mechanisms by which it does so. The plates are essentially the surface expression of the Earth's cooling process. They are not moving because they want to. They are moving because heat must flow, and this is the most efficient way for it to happen. But efficiency in geology does not mean speed. The mantle convects at rates measured in centimeters per year. The Earth has been cooling for billions of years and will continue cooling for billions more before its interior becomes solid and inert like Mars. In the meantime, the plates will keep moving, driven by this inexorable thermal gradient, this slow bleed of heat from core to crust to space. It is a process so gradual that it might as well be invisible, yet so powerful that it shapes the face of the planet. The geology of the seafloor tells this story in layers. The youngest crust is at the mid-ocean ridges, still warm and elevated. As you move away from the ridge, the crust gets older, colder, denser, and deeper. The oldest oceanic crust currently on Earth is only about 200 million years old, found in the Western Pacific. This might seem ancient by human standards, but it is young compared to the Earth's age. Continental crust, by contrast, can be over 4 billion years old. The difference is that oceanic crust is constantly being recycled. It forms at ridges, spreads across the ocean floor, and is eventually consumed at subduction zones. Continental crust, being too buoyant to subduct, accumulates over time. It is the Earth's long-term memory, a record of billions of years of geologic history. Oceanic crust is the short-term working memory, constantly overwritten, never preserved for more than a few 100 million years. This recycling process means that we have no direct samples of the ocean floor from when dinosaurs first appeared, let alone from earlier periods. The seafloor that existed during the Cambrian explosion, when complex life first diversified in the oceans, has been completely subducted and destroyed. The floor of the Panthalassic Ocean, which surrounded the supercontinent Pangaea, no longer exists. It was consumed piece by piece as the Pacific Plate and its predecessors slowly shrank. What we know about these ancient oceans comes not from the seafloor itself, but from indirect evidence. Sedimentary rocks deposited on their shores, fragments of oceanic crust thrust up onto continents, and the magnetic and seismic signatures of their subducted remnants still sinking slowly through the mantle. Geologists have used seismic tomography, essentially a CT scan of the Earth's interior, to image these subducted slabs. The technique works by tracking how seismic waves from earthquakes travel through the mantle. Waves move faster through cold, dense material like subducted slabs, and slower through hot, less dense material like mantle plumes. By analysing thousands of earthquakes recorded by seismometers around the world, geologists can create three-dimensional maps of temperature and density variations in the mantle. These maps reveal slabs of ancient oceanic crust that have sunk hundreds or even thousands of kilometres into the Earth. Some slabs appear to stall at the boundary between the upper and lower mantle, around 660 kilometres depth. Others penetrate all the way to the core mantle boundary, nearly 3,000 kilometres down. These deep slabs are the ghosts of oceans that closed hundreds of millions of years ago, still descending, still cooling, still slowly being reabsorbed into the mantle. The lower mantle is a graveyard of subducted plates. It is a vast, high-pressure realm where rock behaves differently than it does near the surface. The minerals that make up oceanic crust at the surface, basalt and gabbro, transform under pressure into denser forms like eclogite. Deeper still, the minerals transform again, reorganizing into structures that can only exist at pressures exceeding those found anywhere else in the solar system outside of gas giant interiors. These transformations release heat and water, which rise upward and contribute to mantle convection and volcanic activity at the surface. The subducted slab is not simply falling passively through the mantle, it is interacting with it, changing it, driving circulation patterns that influence plate motions thousands of kilometers away. There is a kind of poetic justice in the fact that the ocean floor, which seems so permanent and unchanging during a human lifetime, is actually the most temporary part of Earth's surface. A mountain range on a continent can stand for hundreds of millions of years. The Appalachian Mountains, for instance, are the eroded remnants of a collision that occurred around 300 million years ago. They are old, worn down, but still present. The seafloor, by contrast, has a maximum lifespan of 200 million years before it is recycled. If the ocean floor were a human employee, it would have a mandatory retirement age. No exceptions, no extensions. Once your 200 million years are up, you get subducted, melted, and reassigned to the mantle pool. Continental rifting is the beginning of this cycle, the moment when a continent decides, or rather, when the mantle beneath it decides, that it is time to break up. Rifting begins with the upwelling of hot mantle material, which heats and weakens the overlying lithosphere. The continent stretches and thins. Normal faults develop, creating a series of down-dropped blocks called grabens and uplifted blocks called horsts. Volcanic activity often accompanies rifting as magma finds its way to the surface through the thinned crust. The East African Rift is a textbook example of this process in action. It runs for thousands of kilometers from the Afar Triangle in Ethiopia southward through Kenya, Tanzania, and Mozambique. In some places, the rift is a dramatic valley flanked by steep escarpments. In others, it is a broader zone of faulting and volcanism. Lakes fill some of the deepest grabens: Lake Tanganyika, Lake Malawi, Lake Turkana. Each one a long, narrow body of water occupying a tectonic depression. The East African Rift is young, only a few million years old, and it is still in the early stages of development. If it continues to open, which it likely will, it will eventually split the African continent in two. The eastern part of Africa, including Somalia and parts of Ethiopia, Kenya and Tanzania, will become a separate plate. An ocean will flood the Rift Valley, much as the Red Sea has flooded the rift between Africa and Arabia. This new ocean will widen over tens of millions of years, creating a new mid-ocean ridge, a new spreading centre, and a new cycle of seafloor creation and destruction. But this is all in the future, and the future in geology is measured in millions of years. For now, the rift is just a valley, slowly widening, occasionally shaken by earthquakes, dotted with volcanoes, and largely indifferent to the plans and boundaries of the nations that happen to exist along its length. Rifting does not always succeed. Sometimes a rift starts to open, and then stalls, leaving behind a failed rift or aulocogen. The mid-continent rift in North America is an example. About 1.1 billion years ago, the continent began to split apart along a line running from present-day Lake Superior southwestward toward Kansas. Volcanic activity was intense. Thick sequences of basaltic lava flows were erupted, some of which are now exposed along the shores of Lake Superior, but the rift never fully opened. The continent did not split. The process stopped, leaving behind a long, narrow trough filled with volcanic and sedimentary rocks. Why the rift failed is not entirely clear. Perhaps the mantle upwelling that initiated it weakened or shifted location. Perhaps stresses in the plate changed direction. Whatever the reason, the rift died, and the continent remained intact. The mid-continent rift is now a fossil, a scar, a reminder that not every tectonic process runs to completion. The same is true for subduction zones. Not all of them are currently active. Some have shut down, either because the oceanic crust has been entirely consumed or because changes in plate motions have redirected the stresses elsewhere. The Cascadia subduction zone off the coast of the Pacific Northwest is active, but it does not produce frequent earthquakes. The last major earthquake on the Cascadia zone occurred in 1700, a magnitude 9 event that generated a tsunami that struck Japan. Prior to that, the zone had been quiet for centuries. This does not mean it is inactive. It means the plates are locked, accumulating strain, building toward the next great earthquake. The interval between events can be several hundred years. From a human perspective, this is a long time. From a geologic perspective, it is barely a pause. The sedimentary record preserves evidence of past earthquakes along subduction zones in the form of turbidites, underwater landslides triggered by seismic shaking, and tsunami deposits, layers of sand and marine debris carried inland by giant waves and left stranded well above normal high tide. By studying these deposits, geologists can reconstruct the history of past earthquakes and estimate how often they occur. This is particularly important in places like Cascadia, where written records only go back a few hundred years, but the geologic record extends back thousands. The pattern that emerges is one of irregular but repeated events, massive earthquakes every few centuries, with smaller events more frequent. It is a schedule of sorts, though not one that can be relied upon for precise predictions. The plates do not punch a time clock. They release strain when the strain becomes too great, and the timing depends on a host of factors that are difficult to measure and impossible to predict with precision. Paleoseismology, the study of prehistoric earthquakes, is a field built on patience and attention to detail. Researchers dig trenches across fault zones, exposing layers of sediment and soil that have been offset by past earthquakes. Each rupture leaves a signature, a disrupted layer, an offset soil horizon, a colluvial wedge of debris shed from the fault scarp. By carefully mapping these features and dating the layers using radiocarbon or other methods, geologists can determine when past earthquakes occurred and how large they were. It is detective work, piecing together evidence of events that happened centuries or millennia ago, events that left no written record but nonetheless shaped the landscape in measurable ways. The Alps are a product of the collision between the African and Eurasian plates, a process that began around 50 million years ago and continues today. The collision closed an ancient ocean called the Tethys, subducting its floor and crumpling the sediments that had accumulated on its margins into a massive mountain range. The Alps are not a single, simple structure. They are a complex assemblage of thrust sheets, nappies, and fold belts, each representing a different slice of crust that was deformed, stacked, and transported during the collision. Some of these nappies have been thrust northward over 100 kilometers from their original positions. The rocks themselves tell stories of burial and uplift, of journeys deep into the crust and then back to the surface. Metamorphic rocks in the Alps preserve evidence of pressures and temperatures that indicate burial depths of 30 kilometers or more. They were subducted, heated, and then exhumed as the collision continued and erosion stripped away the overlying material. Erosion is a critical part of the mountain building process, though it is often overlooked. Mountains do not simply rise and then remain static. As they rise, they are simultaneously worn down by weathering, rivers, glaciers, and landslides. The material eroded from the mountains is transported by rivers to the lowlands and oceans, where it accumulates as sediment. This sediment load can be enormous. The Ganges and Brahmaputra rivers, which drain the Himalayas, carry over 1 billion tons of sediment per year to the Bay of Bengal. This sediment builds the Bengal fan, one of the largest submarine fans in the world, a vast apron of sediment thousands of meters thick that extends far out into the Indian Ocean. The fan is a record of the erosion of the Himalayas, a record written in layers of silt, sand, and clay. It is also a redistribution of mass. The weight of the sediment in the Bay of Bengal depresses the crust there, while the erosion of the Himalayas reduces the load on the crust beneath the mountains, allowing it to rebound slightly. The system is in a kind of dynamic equilibrium, with uplift and erosion approximately balancing each other over long timescales. Iceland is one of the few places on Earth where a mid-ocean ridge is exposed above sea level. The island sits astride the mid-Atlantic ridge, and it is being pulled apart at a rate of about 2 centimeters per year. This divergence is visible in the landscape. The island is split by a series of volcanic fissures and rift zones that run roughly north-south. The most famous is the Thingvellir Rift, where the North American and Eurasian plates are visibly separating. You can walk between them. You can stand with 1 foot on each plate. The rift valley is steep-sided with cliffs marking the edges of the plates. Over time, the valley widens and new volcanic material fills the gap. Iceland itself is a product of this process, built up over millions of years by repeated volcanic eruptions along the ridge. The island is also affected by a mantle plume, the Iceland hotspot, which contributes additional volcanic activity and causes the ridge to be elevated above sea level rather than submerged like most of the rest of the mid-Atlantic ridge. The volcanism in Iceland is frequent and varied. Eruptions occur every few years on average, ranging from slow effusive eruptions that produce lava flows to explosive eruptions that generate ash clouds and pyroclastic flows. The eruption of Eyjafjallajökull in 2010, though relatively small by geologic standards, disrupted air travel across Europe for weeks due to the ash it produced. The eruption was a reminder that even routine volcanic activity can have significant impacts on human systems, despite being a minor event in the context of the plate boundary's overall activity. Transform faults are perhaps the most overlooked feature of plate tectonics. They do not create new crust like mid-ocean ridges, and they do not destroy it like subduction zones. They simply accommodate lateral motion, allowing plates to slide past each other. The major transform faults on mid-ocean ridges offset the ridge axis, creating a stepped pattern. These faults are sites of intense seismic activity, but because they are underwater and far from population centres, their earthquakes rarely make headlines. The fracture zones that extend away from the ridge axis, on the other hand, are largely inactive. They mark the trace of past transform motion, now frozen into the oceanic crust as linear scars that can be traced for thousands of kilometres across the ocean floor. The Dead Sea Transform is a continental transform fault that runs from the Red Sea northward through the Dead Sea and into Turkey, where it connects with the East Anatolian Fault. It accommodates the northward motion of the Arabian Plate relative to the African Plate. The Dead Sea itself occupies a pull-apart basin, a depression created where the fault bends slightly, causing a local zone of extension. The basin has dropped more than 400 metres below sea level, making the Dead Sea shoreline the lowest point on Earth's land surface. The region is seismically active, with a history of destructive earthquakes. Ancient historical records, including biblical accounts, mention earthquakes in the region, and paleoseismic studies have identified evidence of many more prehistoric events. The fault is not dramatically fast. It moves at only about 5 millimeters per year, but over millions of years this motion has been sufficient to create the topography and structure we see today. Plate boundaries are not always sharp, well-defined lines. In some places, deformation is distributed over a broad zone. The India-Eurasia collision zone is one example. The collision has created not just the Himalayas, but also the Tibetan Plateau, a vast elevated region the size of Western Europe, sitting at an average elevation of over 4,000 meters. The plateau is not a single rigid block. It is internally deformed, cut by faults, and still actively rising in some areas and collapsing in others. The collision has also transmitted stress far into the interior of Asia, reactivating old faults and creating new ones. Earthquakes occur not just in the Himalayas but deep into China and Mongolia, hundreds or even thousands of kilometers from the plate boundary itself. This distributed deformation makes it difficult to draw a simple line on a map and say, here is the plate boundary. Instead, the boundary is a zone, a region of diffuse deformation that spans hundreds of kilometers. The same is true in the western United States. The Pacific and North American plates are sliding past each other along the San Andreas Fault, but this is not the only fault accommodating the motion. There are dozens of other faults. The Hayward Fault, the Calaveras Fault, the Garlock Fault, all of which take up some portion of the plate motion. The Basin and Range Province, a region of extensional faulting that stretches from Oregon to Mexico, is also part of this system, caused by the complex interactions between the plates and the mantle beneath them. The result is a landscape of fault-bounded mountain ranges and valleys, a region that is slowly stretching and thinning, even as the San Andreas accommodates the majority of the lateral motion. The plates are not smooth, their boundaries are not neat. The Earth is messy, and its tectonic processes reflect that messiness. But despite the complexity, the basic principles remain simple. Plates move, driven by heat from the interior. They interact at their boundaries, and over time these interactions shape the surface of the planet. It is a system that has been running for billions of years and will continue running for billions more. It is the longest running, slowest moving, most reliable shift schedule in existence. There are no shortcuts, no speed-ups, no hacks. The plates will take their time, as they always have, and the world will change around them at a pace too slow for any human to perceive, but too powerful for anyone to stop. The next story is about to begin. Please relax and enjoy.